Okay, good evening. Can you hear me? Hello.
Hi. Yes, sir. Yes, sir.
Oh, is it? Can you hear me? Yeah. Good evening, everyone. Let's get started. So, last class we have introduced dependent sources, and I mentioned that there are 4 types of dependent sources: voltage controlled voltage source, which is voltage amplifier; voltage controlled current source, which is transconductance; current controlled voltage source, which is trans resistance; and current controlled current source, which is the current amplifier. And I mentioned that when I mentioned the definition of an amplifier, I said that basically an amplifier is used to improve the strength of a signal. It is meant to make a weak signal. From a weak signal, you need a strong signal, a strong output to drive a load. But that alone is not enough, right? The strength. To get the strength, there is something to do with impedance matching. That means before connecting the load, you might have a signal, but the moment you connected a load, the whole signal drops. For example, if the output impedance of an amplifier is suppose 10 kilo ohm, and the load that you are connecting is only 2 ohms, and you applied a signal. When you apply the signal, and this signal is in voltage form, most of the signal is dropped in the series arm. Nothing goes to the shunt arm. So this voltage is almost zero. So when the whole signal can be transferred, one, the output resistance should be much, much lesser than the load resistance, right? If the signal is in voltage form. Otherwise, the signal is going to get transferred in current form, not in voltage form. So on this, we have classified 4 conversions: V to V, V to I to V, and I to I. So before connecting the source, before connecting the amplifier input, whatever the source was giving a signal, the same signal is expected even after connecting, right? So how is this possible? This is possible if you want to transfer a signal in voltage form, voltage to voltage, from the input to output, your input resistance should be high and your output resistance should be low. If you want a conversion from current to current, right? Like the common base amplifier, your input resistance should be low, the output resistance should be high. If you want input in voltage form but output in current form, then both should be high. If you want to convert from current to voltage, both should be low, right? So an amplifier was classified not on the basis of gain, but on the basis of its impedance matching. And there are 4 ways of impedance matching. If your input resistance is high, I call this amplifier as a voltage controlled amplifier. If the input resistance is low, I called it current control. If the output resistance is low, then I call the amplifier as voltage source. If the output resistance is high, I called it current source. So when do you say that an amplifier is a voltage controlled amplifier? If its input resistance is high. When do you say that an amplifier is current controlled, CC, current controlled amplifier? If its input resistance is low. When do you say that you have designed a good voltage source? The output resistance should be high. When do you say that you have designed a good current source? Your output resistance, the output resistance should be low for voltage source and the output resistance should be high for current source. In fact, if you ask me, 90% of analog discussion runs on building good current sources. So there are so many currents, all current mirrors are current sources. Differential amplifier needs current source. RAM generators need current source. Triangular wave generators need current source. So 90% of analog discussion runs on building good current sources. So you have to see how to get a high impedance. All those structures, they give high impedance. That is why they are called current sources. So if your output resistance is low, it's a voltage source. Output resistance is high, it's a current source. Now if you want VCVS, VCVS means high-low. VC is high, VS is low. High-low is voltage control voltage source. Voltage control voltage source. Low-high, current control current source. High-high, transconductance, voltage control current source. And low-low, current control voltage source. So these are the 4 types of amplifiers, right? And then I said it's impedance matching is one aspect. The strength of an amplifier is the other aspect. And what is the last category? Very, very important. I mentioned that it's not that all the signals can be amplified, right? So when you're applying a signal, most of our amplifiers, they work as low pass filters. Low pass filters in the sense, there is something called a cutoff frequency beyond which the amplifier does not work. So most of our amplifiers, they want to eliminate the high frequency noise. So there is something to do with the frequency reach of an amplifier. So who decides the cutoff frequency of an amplifier? The cutoff frequency of an amplifier is decided by tau, right? Tau is very, very important. Strength of an amplifier, AV, AI, AP. Impedance matching, I told you, impedance matching. Who decides impedance matching? Rin and R0. And the last 3rd category I mentioned was the frequency reach of an amplifier or bandwidth. How do you calculate bandwidth? Bandwidth is simply calculated by the formula. Bandwidth is equal to 1 by tau, right? Or omega 3 dB is simply equal to 1 by tau. And what is tau? Tau stands for R equivalent into C equivalent. R equivalent multiplied by C equivalent, right? Okay. Now, given an amplifier, how do we calculate the input resistance by Ohm's law? Calculation of input resistance or input impedance. How do you calculate? Given a 2-port network or an amplifier, how do you calculate the input impedance? For calculating input impedance, the procedure is connect a test voltage, VT, find IT. By Ohm's law, Rn equal to VT by IT. So here you can connect a known voltage source VT, find IT. So by Ohm's law, what is Rin? Rin as seen by the voltage source, right? So the voltage source is seen from here, from this side. So Rin is VT by IT. So this is very, very important, right? Whenever you want to calculate input resistance, we all know that resistance is nothing but the ratio between the voltage applied and the current drawn from the positive terminal. Rin equal to VT by IT, right? Now, how do you calculate the output resistance of the amplifier? Calculation of output resistance or output impedance are not. So who sees this R naught? The R naught is seen by the load. So it is a load who's trying to see from here, from the output port. So how do we calculate R naught? For calculating R naught, the procedure is first step, step one. Step one, open circuit RL. Open circuit RL, because RL is a confusion. It is seen by RL, so you have to connect a test voltage at this port, right? Open circuit RL. Then when you are seeing from here, if there is a current source, then the current sources, I told you, what is a voltage source in an amplifier? An amplifier is called a voltage source if ideally its output resistance is 0. So these voltage sources should be replaced by short circuit. If it is current source, for finding the output resistance or the Thevenin's resistance, whatever you call it, current sources, the output resistance of any current source is what? Current sources will offer high output resistance. So whenever you're doing Thevenin's equivalent, the output resistances are high for current sources and for voltage sources they are low. So please see that voltage sources are replaced by short circuits and current sources are replaced by open circuit. So it's a simple thumb rule. If somebody says, how do you kill sources? How do you kill sources? You simply say that just short voltage source or open circuit current source, right? So the second step is short circuit VS, short circuit VS, step 3. Step 3, connect a test voltage VT. Some networks books say that just for simplicity, you can make VT as 1 volt. If you make VT as 1 volt, then what will be the R naught? R naught is simply going to be VT by IT, or rather reciprocal of the current, because the voltage is 1 volt. Oh my God, something happened again. So after short circuiting voltage source, you can connect a test voltage here, Vt equal to 1 volt, and find IT. So this is the setup. By Ohm's law, R naught equal to 1 volt by IT. So for calculating of output resistance, let me mention this. The first step is you have to open circuit load. So you can see here, I have open circuited the load. The second step is short circuit the voltage source. Short circuit the voltage source, right? So you can see here that I have short circuited Vs. Then the last step, very important step is you connect a test voltage Vt equal to 1 volt at the output terminals, connect 1 volt at the output terminals, right? Then by Ohm's law, R naught equal to 1 volt by IT. So this is the procedure for calculating the input resistance. You have to apply a test voltage at the input. Rin is Vt by IT. But for output resistance, you have to change the setup. How do we change the setup? We have to connect a voltage source. Before that, please open circuit the load. The reason why we have to open circuit it, this is pertaining to the amplifier. The output resistance is for the amplifier. Whenever you are calculating output resistance, do not include the load. Similarly, whenever you are calculating input resistance, do not include the source. Do not include the source internal resistance. You have to see only at the input port of an amplifier. Never include Rs for input resistance. Never include RL for output resistance. But input resistance is a function of RL. Input resistance is going to change when RL changes, and output resistance is going to change when RS changes. So because you are seeing from the output side, are you getting right? So this is very important. You have to just change the setup for output resistance. For output resistance, just open circuit the load, short circuit voltage source, and then connect 1 volt source at the output terminals. By Ohm's law, R naught is Vt by IT or 1 by IT. 1 by IT. Right? So this is the procedure to calculate input resistance and output resistance. Now, how do we calculate tau? Calculation of time constant. Time constant is denoted by tau. Because if you know how to calculate tau, R and C, then inverse of this time constant is going to be the bandwidth. Calculation of time constant. So three calculations are important for an amplifier. AV, AI, AP, right? That is for the strength of an amplifier. For impedance matching, Rin and R0 calculation is important for an amplifier. And the last important factor for an amplifier is the frequency reach or bandwidth. To know the bandwidth of an amplifier, we have to find tau, time constant tau. Then how do we calculate tau for these simple circuits? And the same thing we are going to extend for bigger and bigger problems. Like if you know how to calculate tau here, the same procedure we are going to extend even for big structures like the common emitter, cascode, double cascode, whatever, so on and so forth. Okay, so let's calculate tau. We all know that tau is equal to R multiplied by C. R into C is tau, right? So before we calculate tau, if there is a voltage source, we will short. If there is a current source, we are going to open circuit. So once I short circuit the voltage source, have R here and C here. Now, at between these 2 points, if you look through the left side here, then you can have R equivalent. And if you see the right side, you can have C equivalent. And what is tau? Tau is going to be R equivalent multiplied by C equivalent. Tau is going to be R equivalent multiplied by C equivalent. And for this simple circuit, R equivalent is going to be R and C equivalent is going to be C. So tau is simply R multiplied by C. It is going to be R multiplied by C. But for this problem, if I short circuit the voltage source here, this R1 R2 and here you have C. You can have R equivalent here, and you can have C equivalent here. So what is R equivalent? These two resistors are in parallel, so it is R1 parallel with R2. So what is tau in this second problem? In this problem, the tau is going to be R1 parallel with R2, which is R equivalent, and C equivalent is C. This is the value of tau. Whereas here, tau is nothing but simply R into C. R into C. Now we have to short circuit the voltage source. When you short this node, becomes this node now, right? So these two resistors are going to come in parallel. They are going to come in parallel. And R equivalent is R1 parallel with R2. So R1 parallel with R2 into C. Now, suppose if I treat this as the ground node, what is the voltage at this point with respect to ground? It is Vs. The voltage here is Vs. The voltage here is Vs. All right. So it is Vs, the same Vs, because we know in a parallel connection, the voltage remains same, right? So it's the same Vs. Now, can I draw the same circuit in this fashion? I mean, just for your convenience, otherwise we can directly calculate. So here we have Vs, and it's the same Vs here. Now, what is the procedure? We have to short circuit the voltage source. You have R2 and this node is this. Now, the moment you short circuit, you can try to bend this resistor just parallel to R1 here. The R1, because this node, suppose this node is X, this node is also the same X, right? So you can, this the same node here, this is X. And suppose this node is Y. So between Y and X, we have R2. Between Y and X, we have R2. And between the same Y and X, we have R1. Between Y and X, we have R1. So these two resistors are in parallel, right? So the same X. You can short here. Here, suppose this is Z. Between Z and X, we have C2. Between Z and X, we have C2. Between Z, if this is X, this node is also X, right? The same node. Between Z and X, we have C1 also. So you have to just bend that resistor because there is a short there, right? Just for your convenience. Now, this is R equivalent and this side we have C equivalent. Now tell me, what is R equivalent? R equivalent is going to be R1 parallel with R2. What is C equivalent? See, if two capacitors are in parallel, what is the equivalent capacitance? It is addition. So tau is going to be R equivalent into C equivalent, which is R1 parallel with R2 into C1 plus C2 into C1 plus C2. So what is the time constant here? R1 parallel R2 into C1 plus C2. So this is the time constant. But for a common emitter amplifier or for a common source amplifier, the technique that we are going to follow is, I told you, to make the subject more simple, we will alleviate the problem one by one. One by one, in the sense, we don't directly jump into the total C equivalent and total R equivalent. We will take one capacitor at a time. We will do slowly there, right? Suppose 3 capacitors are there and the circuit has 3 time constants. We will calculate tau 1 first, tau 2 first, tau 3 first. But whenever you are calculating time constant due to one capacitor, what we should do to other capacitors? The other capacitors should be replaced by open circuit, This method in textbooks is called the open circuit time constant method. So the same problem, I will do it because answer we already know, R1 parallel R2 into C1 plus C2. But this is not the procedure we will follow for amplifiers. The standard procedure or very popular best approximation procedure is an open circuit open circuit time constant time constant method we will follow. That means we will take one capacitor at a time, C1 alone. When I take C1 alone, C2 should be replaced with open circuit. If I take C1 alone, C2 should be replaced with open circuit. This procedure we will follow for common source, common emitter, all those amplifiers, right? C1. And C2 is not there. I just removed C2. It is an open circuit. Now we will short circuit the voltage source here. Then these two resistors will come in parallel. R1 parallel with R2. And here you have C1. Now we have to calculate tau 1. Tau 1 equal to R1 parallel with R2 into C1. Into C1. Right? Then what do we do? We take C2 alone. C2 alone. with C2 alone, if you short circuit Vs, then tau 2 is going to be R1 parallel R2 into C2. Then what is the total tau? Tau 1 plus tau 2. So tau is going to be R1 parallel with R2 into C1 plus C2. This procedure we are going to follow in future. So we will take one capacitor at a time. First C1 alone. Then the time constant offered due to C1 is going to be R1 parallel with R2 into C1. With C2 alone, it is R1 parallel R2 into C2. And the total delay offered by the system is the delay offered by individual poles. Right? Suppose an amplifier has got 3 time constants. Simple way to calculate bandwidth is what? Take the individual poles, tau 1, tau 2, tau 3, add them, you get the total delay offered by the system, and the bandwidth offered by the amplifier is simply equal to 1 by tau. I'll give you a simple example here. How to apply this concept in amplifiers. How to apply this concept in amplifiers is in future, not I'm just giving you an example that we have. That's the reason I've introduced them in the introduction. In future, Yeah. Now, we'll go back to the previous slide. Yeah, we'll go back to the previous slide here. Now, in the previous slide, I told you a procedure to calculate the time constants, right? R1 parallel R2 into C1 plus C2. Now, the point is how to apply this concept in amplifiers. This is something which we are going to do in future. So, at the input side, you can calculate tau1 at this capacitor. For C2, you can calculate tau2 here. And here you can calculate tau3. What is tau? It is R into C. That's all. This resistance multiplied by the capacitance. So this is something we are going to do. Then what is the total tau? The total delay offered by the system is equal to the delay offered by individual poles or individual capacitors. So the total tau is going to be tau1 plus tau2 plus tau3. See how simple it is, right? Now we can make it complicated. So this is the best approximation we are going to follow. How we can make it complicated is you can take the small signal model of a MOSFET, a small signal model of a MOSFET, and then you can apply Kirchhoff's laws and two-stage amplifier, you know how much time does it take. But instead, what I'm saying is just look at the amplifier and tell the bandwidth. So how do we tell the bandwidth? You know, R1 into C1 is tau1, and similarly tau2, tau3 we will calculate. And by inspection, we can simply say bandwidth is 1 by tau, or 1 by tau1 plus tau2 plus tau3. But if you say that, no sir, I want to individually calculate omega 1 equal to 1 by tau1, omega 2 equal to 1 by tau2, then also it's okay. But ultimately, this is something you're going to write. Tau1 is nothing but 1 by omega 1, 1 by omega 2 plus 1 by omega 3. So it's all waste of time, right? So you simply say that bandwidth is 1 by tau. That's all. Anytime you find an amplifier, what is bandwidth? The bandwidth is simply 1 by tau. What is tau? It is the summation of tau is going to be the summation of the total delay offered by the system is the delay offered by individual capacitors. So this is the easiest thing, right? But the same concept, you can make it very complicated if you draw the high frequency model of a MOSFET or the BJT, and you know high frequency model, and then keep on doing, and finally you get the same answer, right? So analog is all about intuition. I told you, by looking at the amplifier, you have to assess the gain. So I'll tell you still lazy method. What is the still lazy method is, suppose you know, you are gut sure that tau1 is 1,000 times more than tau2. Tau1 is 1,000 times more than tau2 and tau3. Then what will you do? Tau1 plus tau2 plus tau3, then it is approximately equal to tau1. That means what? By looking at the amplifier, you directly go to the pole that is dominant. This is the dominant pole approximation. That means you are gut sure that you don't care about all the other capacitors, and you care about, by looking at the amplifier, you just care about, okay, there is one capacitor which I know will give you the largest delay in the system. Just go and do tau is equal to R into C, and bandwidth is 1 by tau. That's it. That's the best dominant pole approximation you can do, right? But this is also fine. This is also fine. The total delay offered by the system is the delay offered by individual capacitors. You have to take tau1 and tau2 and tau3. This way, you can avoid the high frequency model and all that stuff, right? But initially, I will do by high frequency, and I'll show you that how this method is going to finally give you the same answer, right? So I repeat, what is our time constant method that we are going to follow? I would lightheartedly call this method as the open circuit time constant method. Why is it open circuit? Because when I consider C1, C2, C2 and C3 are replaced by open circuit. So tau1 becomes R1 into C1. Similarly, we calculate C2 and C3, and then we add them. And the bandwidth is simply equal to 1 by tau. So this is what we are going to do again and again and again using MOSFET, BJT, and op-amp. Are you getting right? So because 90% of analog runs on amplifiers, and what do we do in amplifiers? We calculate the currents and voltages, we calculate the input and output resistances, and we calculate the frequency reach of the amplifier, right? Okay. So this is something we are going to apply in future. So don't worry about this. I'm underlining here. This is not today. We are going to do this in future. And you know how much time does it take? This takes lesser time than the previous problem that we have done, right? So because why the previous problem is, why this problem is complicated and MOSFET is simple? Can you understand here why this problem is difficult to do by a student, but the MOSFET problem is easy to do? Why? Because MOSFET offers isolation. MOSFET offers isolation. The input resistance of MOSFET is infinite. It's almost like an open circuit here. So when you're doing with C1, you're least bothered about C2, C3. When you're doing with C2, you're least bothered about C1, C3. When you're doing with C3, you're least. So you almost imagine that this is the only network available, so you calculate R into C. So it's like child's play. Whenever the moment an amplifiers are introduced, because of their high input resistance or low output resistance, they provide beautiful isolation. So you can individually calculate the time constant by these capacitors, right? So that way, the circuit might look complicated, but the analysis is very, very simple, very simple. Okay, now, what sort of a device is an amplifier? I told you that an amplifier is a two-port device. What do you mean by two-port? At the input port, we give a signal, and at the output port, we connect a load. So this amplifier is a two-port network, right? Now, just imagine your cell phone is there, and you're talking, or an amplifier is there, a microphone, you're talking through a microphone. That's the input port. The speaker is the output port. But can you imagine an amplifier without a power supply? Or can you imagine a cell phone who's giving input and output, but there's no battery in a cell phone? So it is the battery in a cell phone which decides whether the cell phone is working or not, right? If the battery is not functioning, then the output, there's no question of output, even if you keep on talking through a cell phone, right? So it is this power supply who's going to decide the transfer characteristics. So strongly, in my opinion, an amplifier has got 3 ports, not physically, not 2 ports, 3 ports. What are the 3 ports in an amplifier? One is input port, where you connect the microphone. The second one is the output port, where you connect the load. But very, very important is the power port. There is a rail, power supply rail, which actually decides the transfer characteristics. So that is very important. Power supply, and the transfer characteristics. Power supply and the transfer characteristics. So an amplifier has got 3 ports. And first today, during the syllabus, I've drawn an amplifier. If you remember, I've drawn an amplifier, but this amplifier had a supply here, supply. Suppose there's 5 volt and I have a now you tell me for whatever input that you apply, can you expect an output more than 5 volts? Because in electronics, I repeat, in electronics, output will not come from input. In electronics, output is not coming from the input. Output always comes from the power supply. Who supplies power to the amplifier or who supplies power to the load is the power supply. Why is it called power supply? Because he supplies power. Without the power supply, there is no question of output. Now tell me, can you expect an output more than 5 volt? It's not possible, right? So suppose you might give a small 1 millivolt signal. At the output, this is Vin. At the output, you might get a big signal, but this signal swing is say 2 volts peak. Suppose you have given an input like this. You got an output which is like this, which is a 3 volt peak. You have given an input, you got an output which is 5 volt peak. But if you give a signal, can you expect 10 volt? No, it's not possible. This is going to be the maximum. But the signal swing maximum is 5 volt. Who is deciding this? This is decided by whom? It's decided by the power supply. So let us first draw step by step the transfer characteristics of an amplifier, right? The transfer characteristics of an amplifier. Okay. What is the symbol of an amplifier? Forget about BJT. We'll have a simple schematic for an amp. What is a simple schematic of an amplifier? This is the schematic of an amplifier. This is an amplifier. See how simple it is, right? If I put 1 in the middle, then it becomes a buffer. If I put 1, it becomes a buffer, right? Right. K. What does K stand for? Gain, right? Gain. This is input, this is output. V0 is K times of input. Now, as Vin increases, your V0 will also increase. But who decides the maximum V0? The maximum V0 is decided by the limits here. So I'll come back here. I'll come back to that slide again. Let me make it like a simple problem. Draw the transfer characteristics right of this amplifier whose gain is 1. This is buffer Vin. So what does this line indicate? This is input, this is output. These arrows, they indicate the supply rail voltages. I'll make it 10 and minus 10. So how do you draw the transfer characteristics? V0 is equal to 1 into V, K into V. So V0 is 1 into V. So this is of the form Y equal to mx. Y equal to mx. So what is the slope m here? The slope m here is 1. The slope m here is 1. So how do you draw the transfer characteristics? Now y equal to mx is a straight line passing through the origin, right? What does this line indicate? If V in is 1 volt, your V naught is also 1 volt. If V in is 5 volt, your V naught is also 5. If V in is minus 1, your V naught is minus 1, right? So this is the line indicating. But how long will it go? Till it touch the sky? No, is it not? What is the maximum output for any nasty input that we give? What is the maximum output that you expect? The maximum output is only the supply rail voltages. So once you give 10 volt, the output is also 10. But if you give 11 volt, it's going to stay at 10. If you give 11, it's going to stay here. So this is the transfer. The transfer characteristic says that you might change your input to whatever value that you want, but please don't expect an output more than how many volts? 10 volts. Now, what happens if my input Vin is 2 sin t? What happens if Vin is 2 sin t? If Vin equal to 2 sin t, then my V naught is also 2 sin t. If Vn is 2 sin t, then your V naught is 2 sin t. Now, any guess what happens if Vn is 12 sin t? What will be your V naught? If Vn is 12 sin t, what will be your V naught in this transfer characteristics? Now, what happens if I apply a sine wave here? if I apply a sine wave of 2 sine t, then there is a corresponding point here which gives me the output also as 2 sine t. But what happens if my output stops at 10 volt? I told you my output stops at 10 volt. What if my input is 12 sine t? This is 12 volt, 12 sine t. But you can see here, after 10, my output is always 10. So if I give 12 sine t, 12 volt, then my output is going to clip at 10 volt. Why it has got clipped? Clipping is a distortion. Clipping is a distortion. That means you cannot get any output more than the supply voltage. Suppose, see, there was a gate problem, I remember. The supply is 5 volt and the examiner asked a DC output voltage. And in the options, there was 1 volt, there was 7 volt, there was 9 volt, there was 15 volt. So some of the students, they have not even solved the problem. They simply said 1, right? And I asked them, how did you do it? Sir, there is no need to do because supply is 5 volt. But in the options, 5 volt is there, 7 volt, 9 volt, 15 volt is there, 1 volt is there. So 1 volt is only possible. See, output cannot be more than 10 volt. The reason is I have given the supply as plus 10 and minus 10. So it is unlikely that you cannot get 12 sine t at the output, right? So what is clipping? Clipping is a distortion. What is distortion? If the shape of output is not similar to the shape of the input, then we say distortion has occurred, right? There are so many forms of distortion, crossover distortion, a lot of distortions are there, but the basic fundamental distortion is clipping, right? This we will see during the lab sessions, especially when the students come, right? First lab session, a student finishes off, he changes the controls and he leaves. The second lab session, another batch of students will come, and the moment they give an input, signal is getting clipped. Then they'll call the lecturer. What the lecturer will do? Nothing. He'll just decrease the input. That's all. So how do we avoid distortion here? Very simple. The input signal, whatever is there, you have to slightly decrease. When it decreases, he will see, sir, distortion is gone. How did you do that? There is no big magic. You, as an engineer, how can you avoid distortion? You can proudly say that I can avoid distortion, I can eliminate distortion just by decreasing the input. Because more input does not mean more output. So output does not come from input. Input is meant only to control the characteristics of the device. Output always comes from the supply rail voltage. If it is plus 10 and minus 10, you cannot expect 12 volt, right? Simple. Suppose your battery, your cell phone battery is 4 volt. At any node inside the cell phone, at any node voltage inside the cell phone, there will be millions of nodes. Can you expect 8 volt, 9 volt, 10 volt inside any cell phone? Unlikely, because the battery itself is 4 volt. How you can expect 8 volt inside the cell phone at any node, right? So output always comes from the supply. So it is the power supply who is going to decide the supply limits. Now, why don't you draw for gain 10, draw transfer characteristics for gain equal to 10, right? So I'll put 10 here in the box triangle. This is output, input. You can take the same sum, plus 10 and minus 10. And what happens for gain 10 lakhs? The gain equal to 10 power 6, because op-amp has 10 lakhs gain. Oh my God. How will you draw the transfer character? V naught equal to 10V. The slope is 10, right? Now see here, if the gain is more, it puts a lower limit on the input, because previously when V in was 10, your V naught is 10. But if V in is 10, your V naught is going to be 100. It's not possible. So your V in has to be only 1 volt when your V naught is 10 volt. So now, in the previous example, what are the two sine waves we have given? One is 2 sine t, the other one is 10 sine t. So 2 sine t was lucky, 10 sine t the signal got clipped. But for this present problem, can you give 2 sine t? You cannot give. Because what is the limits now? The limit here is only between +1 and -1. If you give any voltage more than 1 sine t, then definitely the signal is going to get clipped. So as the gain increases, it puts a lower limit on the input that we are applying, right? What happens if the gain is 10 lakhs? V naught is going to lie between -10 and +10. And what is the range of V in? -10 by 10 lakhs to +10 by 10 lakhs. So it's very, very V in, V naught, because what is the relation between output, input and gain? Input is output by gain. Input is output by gain. So now 10 by 10 power 6 is almost here. So somewhere here, right? So this is how the characteristics of an op amp looks. As the gain keeps increasing, it puts a lower limit on the input. So you can imagine 10 by 10 power 6, that's a very, very small number, right? So what is the conclusion here? Conclusion. So if an amplifier works with if an amplifier works with two supplies, plus V and minus V, to avoid distortion. Oh my God, now my handwriting is also changing. To avoid distortion, the input range, V in range, has to be between, this is a gate bit, minus V by K to plus V by K. To avoid distortion, your input range should be minus V by K to plus V by K. Okay, so let me repeat. An amplifier strictly has got three ports. One is the input port, the output port, but the output does not come from input. Input is only meant to control the characteristics. So output always comes from the supply. So it's like a battery in your cell phone. Without the battery in your cell phone, the output is not going to occur, right? So you get an output only when there is a battery. But what is this going to do, the supply? The supply is going to decide the swing limits of the output. Is going to decide the swing limits of the output. If you have a single supply, then what is going to be the transfer characteristics? If you have a single supply, one end is ground. For whatever input that you give, your output is going to lie between 0 and 5. But in the previous example, I have given plus 5 and minus 5. So it's going to swing between plus 5 and minus 5, or plus 10 and minus 10. So this is, if you have a single supply, and then there is no question of a negative voltage. See, this also happened. Once there was a BJT problem, it has got only one positive supply, and there were around 2 negative answers in the options. So you can blindly eliminate them because the output cannot be less than 0, which is ground, and it cannot be more than 5. So the output swing is going to be between 0 and 5 volt, right? So the output always comes from the supply. See, this is something like this. Suppose you have just as an example, 15 volt and 3 resistors are there. 3 resistors, 1K, 1K, 1K. 1K, 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 right? Then how much voltage each resistor will drop? It will drop 5. This will drop 5 and this will drop 5. Am I right? Because 5 plus 5 plus 5 is 15. Now, when it comes to analog, we don't draw a circuit like this. We don't have a loop. Instead, we draw it like this. We draw it like this. We say, I am giving 15 to 3 resistors. I am giving 15 to 3 resistors, 1K, 1K, 1K. Now, what is the voltage at this point? 15 minus 5 is 10. So the voltage at this point is 10 volt. The voltage at this point is 5 volt. This is 0 volt. So 0, 5, 10, 15. As you go up, so this is a simple way of looking at a problem. When you look at a problem, you say this is ground and this end is 15. So this is 15 volt. But here you have only 10 volt. But here you have 5 volt with respect to the ground, right? As you move up, so whenever a transistor problem is given, as you move up, the voltages will be in increasing order, right? So if somebody gives you a transistor problem with 4 or 5 transistors, as you go up, you can simply say that the node voltages are what? Increasing, right? What is the current here? 15 by 1K, 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 15 by 3K. So that is 5 milliampere. 5 milli into 1K, 5 volt. This is 10 volt, 50. So this is how we write, right? So suppose instead of this 1K, you have a transistor here. So you can replace that with a suppose I put a transistor here, it doesn't matter. If I put a transistor, so can you expect this output to be more than 15? So there's no logic in it, right? So people will laugh if you say that across this transistor you have a 20 volt or 30 volt. It's not possible because the output is always has to come from the supply, right? So let's keep that in mind. Okay, so now we have seen how to draw the transfer characteristics. Now, what happens in an amplifier? This is a special case. What happens? You have an amplifier whose gain is 1. You have an input here, output, and somebody has connected a resistor in between, an ungrounded resistor. The gain is 1. Now, this resistor, you can blindly remove it and do the analysis. So you can just blindly say that, sir, I don't want to consider this resistor. This is going to save some time for me in the exam. So just remove that resistor and then do the rest of the work. Suppose this gain 1, who is gain 1? Some example, suppose a common collector amplifier is there. Between the input and output of a common collector amplifier, somebody has put a resistor. You can blindly remove that resistor and do the analysis. Now you might say, why we should remove that resistor? I told you last class, current 0 means open circuit, voltage 0 means a short circuit, right? So if gain is 1, V0 equal to V. V0 is equal to V. Now you want to calculate the input resistance of the amplifier. Input resistance. And imagine that the amplifier that you have connected has got high input resistance. So the only way this current can flow is through this resistor. Now tell me, if this node is Vin and the output is again equal to input, current needs a potential difference, right? So what is I in? I in should be V in minus. So I told you Ohm's law. What is Ohm's law? If you have R, this is V1 and V2, there is a current I. First class I told you. What is I? It is V1 minus V2 by R. I is V1 minus V2 by R. So I in is V in minus V naught by R. But what is V naught? V naught happens to be V in. So the current is zero. Current is zero means this resistor R, you can treat it like an open circuit. Physically, there will be a resistor, but you are trying to imagine that there is no resistor, and we are doing the network analysis, the calculations, right? It will save time. But if somebody asks you, is there a technical name for that? No, how did you remove that resistor? You can say that this resistor experiences bootstrap. There's a fancy word, right? Don't worry, nothing. You just removing that resistor, and somebody says that, no, how are you able to do that? You can proudly say that, I'm applying a technique called bootstrap. That fellow will get worried. No, it's such a fancy word, but then there's nothing there. This resistor at both ends is experiencing same dynamics. Suppose I apply a signal. Suppose I have a resistor. I apply a sine wave here, and the same sine wave is manifested here also. What will be the current? So any signal that I apply, if because of the amplifier gain 1, the same signal is here, then the current is going to be 0, right? So you can blindly remove that resistor and just, so you see, it depends. If you don't remove that resistor, there'll be an additional loop, and suppose 2 students are there, student 1 and student 2. Just tell me who is clever, student 1 and student 2. Student 1 removes that resistor, so the number of loops have reduced, so he's quickly calculating. Student 2, he is still considering that resistor and doing the network analysis. And finally, in the end, last step, he came to know that the current there is 0, right? So the first student, who the moment he sees a problem, he recognizes that this is an unwanted element here. I don't have to look at this element, just throw that element and calculate. He will save more time, right? And what is the technical word? What is the technical thing that he has applied there? He has applied a technique called bootstrap, because the circuit lifts with its own bootstrap. So the input and the output both are experiencing same dynamic. So suppose my input is a signal, right? Is a voice signal, and the output is also moving by the same amount, right? Because V0 and V in both are same. Then what will be the current that is flowing through that resistor when both nodes are experiencing same dynamic? Suppose there's a sine wave here, both are moving like this, right? So if one end goes at 1 volt, the other one also goes at 1 volt, right? The net effect is that the current always needs a potential difference. So there is no potential difference, no current. When there is no current, there is no, when there is no current, it is as good as it is an open circuit. So what is this technique called? The technique is called bootstrap, right? Now, what happens if this is not 1, it is -1? What does negative sign indicate? What does negative sign indicate? Suppose I have -5. How do you sketch this? -5, V in. Your V0 is -5 in. What do you mean by this negative sign? The negative sign indicates what? It indicates phase shift. So if I give 1 sin t here, your output is going to be -5 sin t. So if I apply any signal, that signal is going to flip by 180 degrees. So this is 1 volt. This is going to be 5 volt. Are you getting? Of course, this has to be limited by the supply limits, right? You cannot extend it as you wish. So negative sign indicates phase shift. Phase shift. Negative sign indicates phase shift. Now, such an amplifier now this is more fun now. What happens if I put a resistor between the input and output? Now what happens? Now your V naught is going to be minus 1 into V, or V naught is minus V. Now what will happen to the input resistance? Now what will happen to the input resistance? Tell me. Your current IN is going to be Vin minus V naught by R. It is Vin minus of minus Vin by R. So your Vin by IN is going to be R by 2. R by 2. Now tell me in Ohm's law, when the resistance can decrease. Suppose I have some resistor and suddenly it has decreased. That means what? Maybe the current has increased. Maybe the current, because according to Ohm's law, what does Ohm's law say? Ohm's law, R is V by I, right? R is V by I. So if the current increases by 2 times, if this increases by 2 times, then resistance is going to decrease. So now you can understand why the current has increased. The current has increased because of the potential difference. If one end is 1 volt, if this end of a resistor, is 1 volt, this end of a resistor is minus 1 volt, the current has increased 2 times. 1 minus of minus 1 is 2. So 2 times the current has increased, then the resistance has decreased it. So can you just tell me an equivalent for this diagram where the current has increased by 2 times and the resistance has... So in my opinion, the equivalent for this is 2 resistors in parallel. So this amplifier, which is stuck with a resistor between the input and output, and its gain is 1 with a phase shift, that amplifier is equivalent to 2 resistors, because this resistor experiences I, this resistor experiences I, the total I is going to be 2I, the current has increased by 2 times here. Then what is the equivalent resistance here? It is going to be R parallel with R, which is R by 2, right? So whenever you find an amplifier with a phase shift, but if this is a positive number, if it is a positive number, just remove that resistor. You say that the input resistance is only the resistance of the amplifier. The amplifier has infinite input resistance, it is infinite, that's it. The resistance is not going to offer anything. But now this resistor is going to offer a resistance which is R by 2. What happens if this is 5? If this is 5 in that previous example, if this is Vin, your V naught is going to be minus 5 Vin, and your IN is going to be 6 times. IN is Vin minus of minus 5 Vin by R. What is Vin by IN? It is R by 6. So this is more fun, is it not? So previous example I told you, I'm giving an input of 1 volt, 1 sine t. On the other end, I'm having minus 5 sine t. So if one end is 1 volt, the other end went down by minus 5. So what is the potential difference now? Look at the potential difference from here to here, 6 times, right? So one end goes up by 1 volt. The same instant, this guy comes down by minus 5. If this guy comes down by minus 1, this guy goes up by 5. So at any instant of time, one is going up, the other one is coming down. At any instant of time, the current is 6 times. 6 times you're pumping more current. So can we generalize this? If I'm having an amplifier of gain, okay, then it is R by 6. If I'm having an amplifier of gain A or minus A, it's got a resistor R. Can I say that the input resistance Rin is going to be R by 1 plus A? Because the current is going to increase by 1 plus A times. If it is 5, it's going to increase by 6 times. If it is 1, it's going to increase by 2 times. If it is 3, if it is 10, if it is 10, it is going to increase by how many times? 11 times now, 11 times. So I can say it's R by 11. This is technically called Miller effect. It's a simple logic, right? So you have understood Miller effect by a simple logic that current needs a potential difference. That's it. So whenever a resistor is stuck between the input and output, and you're pumping some amount of current through that resistor, and if the gain is more, you're pumping 1 plus A times of the current, right? 1 plus A times, 1 plus A times, then the equivalent resistance is going to be R divided by 1 plus A, right? So let me put a table and just tell me what are the different amplifiers that we have calculated here. I'll put A here and R in here. Just tell me. Yeah. What if there is no amplifier? What if there is no amplifier? My A is 0, no amplifier. If my A is 0, I just remove the amplifier, throw it. Then what is the resistance seen from here? No amplifier, just throw the amplifier. Then you will see naturally only R, because there's no amplifier at all. But if the amplifier has got a gain 1, this amplifier has got gain 1, and this amplifier is minus A, minus 1, then it is going to be A is 1, so it's going to be R by 2. If A is 5, we have found it as R by 6. If A is 10, then it is going to be R by 11. Are you getting? If A is A, then Rn is going to be R by 1 plus A. So what do we call this effect? This is called Miller effect. It is called what effect? Miller effect, right? What if A is 2? There's another special case here. What if A is 2? Special case. What if A is positive? 2. Negative, we have put a table. 1, 2, 3, all the negative amplifiers we have put. What if it is 2, 3, 4 positive numbers? This is Vin. Your V0 is going to be 2 Vin. Then what is In? In is going to be Vin minus 2 Vin by R. Then Vin by In is going to be minus R. Whoa! See here, beautiful. So this is simulation of negative resistance. Simulation of negative resistance. So all the, except one, the first one is bootstrap. So the moment the gain is 1 and a positive number, you can throw it. But now the gain becomes 2, 3, 4, 5, 6. You're not going to get positive answers hereafter. You're going to get negative answers. Minus R, minus 2R, minus 3R, minus 4R. So if you have positive amplifiers with positive gain and you put a resistor between input and output, then you're going to simulate negative resistance. But if you have a negative amplifier, then you're going to simulate positive resistance. So what is the conclusion here? Ungrounded resistors connected between input and output simulates positive resistance for negative gain and negative resistance for positive gain. But please, Miller effect is usually applied for amplifiers which have a phase shift, like the common emitter amplifier, right? But this is a special case. If you are having a positive amplifier, an amplifier with a positive gain, that, and if you intentionally connect it, this is intentionally done, right? If you intentionally connect a resistor between the input and output, then when you see through the input, the amplifier is simulating, surprisingly, a negative resistance. So what do you mean by negative? yesterday I told you, if I take a direction of current like this, it is 1 milliampere, and the current that is flowing in the opposite direction is minus 1 milli. So what do you mean by negative resistance here? The negative resistance tells that this IN is actually flowing in the opposite direction, in the opposite. Why it is flowing in the opposite direction? Because the potential difference, if you see, who is at higher potential here? Who is at higher potential? Input side or output side? Output side. So the actual current is flowing in the opposite. That is why we are not simulating a positive resistance. We are simulating a negative resistance. So these are all special cases you can practice. So this is the formula. If you have a amplifier with, I will formally derive Miller effect. I will formally derive Miller effect. But I just got an idea that because we have drawn the transfer characteristics here, what happens if you put a resistor between input and output? If you put a resistor between input and output, if it creates a larger potential difference with a larger current, then if the current increases 2 times, resistance will decrease by 2 times. If the current increases by 5 times, then the resistance will decrease by 5 times. If you have an amplifier of gain A, the current will increase by 1 plus A times. If the current increases by 1 plus A times, then the resistance is going to decrease by 1 plus A times. So this is almost like 1 plus A resistors in parallel. So this circuit is going, that means if there are 1 plus A resistors in parallel, how much current they will draw, that much amount of current this circuit will draw. Are you getting why they are equivalent? Because 1 plus A resistors in parallel, if you connect, how many resistors in parallel? 1 plus A, suppose A is 5, 6 resistors in parallel if you connect, how much current it is going to draw for that voltage input, that much amount of current you are going to get here. Are you getting? You are going to draw at the input side here. Suppose this is, you can give me an example, a simple example that is better. A simple example. See here, my amplifier is having minus 5. I'm giving 1 volt here, 1 volt. What is the output here? Output is minus 5 volt. And I put a resistor R. This is 1 ohm. This is 1 ohm. Or this is say 6 ohms. This is 6 ohms. Right? Now, how much current are you going to draw here? I. Tell me. I is 1 minus of minus 5 by 6. How much current you are going to draw? 6 by 6, that is 1 ampere. 1 ampere of current you are going to draw here. Right? Am I right? Now, what I'm trying to say is, if you connect 1 plus A, which is 6 resistors in parallel, 6 resistors of 6 ohms, 6 ohms, 6 ohms, 6 ohms, 3, 4. Then the overall resistance is 6 by 6, which is 1 ohm. What is resistance R? V by I. 1 volt by I. It is 1 by 1. It is 1 ohm. Right? It is 1 ohm. 6 by 6. 6 by 6. It is 1 ohm. So, if I apply the same 1 volt here, this will take some current, this will take some current, this will take some current, this will take some current. This current is going to be 1 ampere. Are you getting? So the total resistance, it is almost like this circuit mimics, it mimics almost like there are how many resistors in parallel? 6 resistors. So it is R by 6. It is going to be R by 6. This equivalent Rin is going to be R by 6. R is already 6. 6 by 6 is 1 ohm. So it is like 1 plus A resistors in parallel. Are you getting? So what do we call this effect? This effect is called Miller effect. I'll give you a proof for that, later, right? Just keep in mind that whenever a resistor is connected between input and output of an amplifier, what is that you have to see? What is that you have to see? You have to first know whether it is a positive gain amplifier or a negative gain amplifier. If it is a positive gain amplifier, you are simulating negative resistance. If it is a negative gain amplifier, you are simulating a positive resistance. What is the value of that positive resistance? That resistance is going to be R divided by 1 plus A, where A stands for the gain of the amplifier, right? So Miller was given the Medal of Honor during the Second World War He has done a lot of work, but he has given a beautiful theorem. We can prove that by simple Ohm's law. And the logic is what? Simple Ohm's law. Current is more, resistance will be less. That's all, right? Current is more because of the gain. So if current increases by 1 plus A times, the resistance is going to decrease by 1 plus A times. Are you getting? Right? So conclusion. If I have an amplifier with gain A and I connect a resistor or an impedance Z, what is the input impedance here? Zn. It is going to be Z divided by 1 plus A. Miller effect is applied only to ungrounded resistors, capacitors, and inductors. Inductors, we know we electronics engineers, we are shy of using inductors because inductors, they are power thirsty. They are bulky. We don't like them. But still, I have mentioned it because these are the three popular passive components, right? Resistor, capacitor, and inductor. Miller effect is applied only to ungrounded resistors, capacitors, and inductors, right? And this Miller effect, we are going to use again and again and again in BJT, MOSFET, and op-amp. And these formulas, see, whatever I have done till now, I'm going to repeat again. And same formula I'm going to ask, right? Again and again. Because these are the three parameters we have to calculate: strength of an amplifier, impedance matching, and the bandwidth, right? So for calculating bandwidth, these formulas are very, very important, right? Is it difficult to remember? If you have R, you can have R divided by 1 plus A, is it not? So you can take up a problem, find R equivalent, L equivalent, and C equivalent. So you can take down this problem, find R equivalent, L equivalent, and C equivalent. See, if a resistor is already grounded, then you know that the equivalent resistance is that value. If it is ungrounded, then you will have two nodes, input V in, and the output is going to be some K times of V in. But when you're looking at input side, the current is going to change. The current is going to change based on the gain of the amplifier. Are you getting? So you should always apply Miller effect only to ungrounded R, ungrounded L, and ungrounded C. So this is one way of converting an ungrounded to grounded. What is the grounded value for this? Is this. What do you mean by input resistance? It is the grounded equivalent. See here. So when I say input resistance, it is as seen by whom? It is as seen by the input, right? So this resistance, I want to have an equivalent as seen by this fellow. That means I want a resistance here. This is R equivalent. R equivalent. So the whole circuit should behave like this. V in and R equivalent. I in. So what is V in by I in is R equivalent. So I want to convert an ungrounded resistor into a grounded resistor such that the whole circuit equivalent as seen from the input side is going to be R equivalent, right? What is R equivalent now? We know R equivalent directly is R divided by 1 plus A. It is 1K divided by 1 plus 10. It is 1000 by 11 ohms. So 1000 by 11 is going to be R equivalent. So now I can connect here 1000 by 11. How much current this I in is going to give? The same amount of current here we are going, the source is going to give I in. This I in and this I in are same. Are you getting, right? So this R equivalent as seen from the input, V by I is what? R. So from an ungrounded, we are imagining if there is a grounded resistor here, it is going to draw the same amount of current provided the impedance or the resistance changes to how much? 1000 by 11 is the R equivalent seen from the input side. Now, what is the impedance form for an inductor? Z equivalent is going to be Z by 1 plus A. What is Z? Z, I can write it SL. SL by 1 plus A. So L equivalent is going to be L divided by 1 plus A. So the second problem is, did I give 100 or 1000? 100. 100 and there is 1 millihenry. What is L equivalent? L by 1 plus A. 1 millihenry. 1 millihenry by 1 plus 100. 1 milli by 101. 1 millihenry by 101. That is the answer. What about capacitor? Z equivalent is Z by 1 plus A. The impedance form for capacitor is 1 by SC. 1 by SC into 1 plus A. This is very, very important. Capacitors, they suffer with Miller multiplication. This is called Miller's multiplication. When all the capacitors are in parallel. So this is a very, very dangerous thing. If you have an amplifier like the common emitter or whatever amplifier, and you have a chota capacitor here, chota capacitor, a small capacitor, that capacitor is going to behave as if it is very, very big. This is 1 microfarad. It's almost 1 farad. This is huge. See, now you tell me what will happen if you find these type of capacitors in future in common emitter and common source amplifiers. If C equivalent increases, then tau will increase. If tau increases, bandwidth is 1 by tau, bandwidth will decrease. So please remember this. Why did I introduce all this concept is not for resistors, please. It is only because of the capacitor, the parasitic capacitor we are going to discuss in future. So whenever you find such capacitors, you have to alert me. As a student, you have to alert me. You say, sir, look at that chota capacitor. That is not chota. It is going to simulate a much bigger capacitor you cannot imagine. If the capacitance increases, then naturally tau will increase and the bandwidth will suffer. Common emitter and common source, they're going to cry because of these capacitors. As long as the capacitor value is high, physically it might be a small value, but the value it is simulating, electrically simulating, is much bigger value, right? So somebody who stands here, what he might think that there are 10 power 6 1 microfarad capacitors in parallel. If you ask this guy, what do you see? What will he say? He says that there are 10 power 6 1 microfarad capacitors in parallel. It's a huge time constant. So if the capacitance increases, the tau value will increase. If tau value increases, the bandwidth is going to suffer, right? So this is dangerous. This is called Miller's multiplication. So these are all the terms, technical terms, which we are going to apply. So tomorrow, if somebody asks you, when we're doing common emitter amplifier, why common emitter does not have more bandwidth, why it is having less bandwidth, then I will repeat this again there, and I'll tell you that C has increased, right? Because C has increased, naturally tau will increase. If tau increases, then naturally the bandwidth is going to suffer, right? So the resistances, they have Miller division. Inductors, they have Miller division. But capacitors is dangerous. They suffer with Miller multiplication. They suffer with Miller multiplication. Whenever you find an ungrounded capacitor, none of the terminal is grounded, then we have to be very careful, right? Because we have to calculate the gain. If the gain is more, there are so many, it's like so many capacitors in parallel. More C, more tau. More tau, less bandwidth, right? So these formulas are very, very important. C multiplied, only for capacitors is C multiplied by 1 plus A. For resistors, it is R divided by 1 plus A. Inductors, it is L divided by 1 plus A. Capacitors, it is C multiplied by 1 plus A. Now, forget about amplifier. I will prove Miller effect now. Again, now we'll take a break now. When I come back, just with simple Ohm's law, I'm going to prove the same thing again, right? I'm going to prove the same thing with simple Ohm's law, a very, very basic Ohm's law. I'm going to give you a proof for Miller effect, right? So now the time is 7 o'clock. So we'll take a 15-minute break, 15-20 minutes, right? I have something, fresh up, and then come. I will prove the same Miller effect once again, right? With basic Ohm's law, right? Thank you. Okay. Okay, so let's get started. Now, how can we explain the same Miller effect? Suppose I have an impedance Z, which is stuck between two nodes, V1 and V2. And here you have three branches, right? Three branches. So it's connected somewhere in the network. Say there is some current Ix flowing here, Iy, and Iz. There's some current I. Now, according to Kirchhoff's current law, the currents entering this node V1 is equal to the currents leaving the node. So what will you write here? Ix plus Iy plus Iz equal to I. Am I right? Now, and suppose the same current I has to leave here. This is say Ik and IL. Then how will you write Kirchhoff's law here? The same current I is again going to leave as Ik plus IL. All right. Any problem with Kirchhoff's law? The sum of currents that enter that node is equal to the currents that leave the node. Now, what I'm trying to say is, if I have three branches like this, and this Z is ungrounded, it is stuck between V1 and V2. What if I connect here a Z equivalent here, or Z1, such that I is Ix and Iy and Iz, such that I don't violate Kirchhoff's law. And I'll see that the same current flows here, I. Then how will you write Kirchhoff's law here? You're going to write Ix plus Iy plus Iz is equal to I. There's no change, please. There's change. But to make them same, this should not be Z, it should be Z1. And we have seen that this Z1 is equal to Z divided by 1 plus A, which I'm going to prove it. That means anywhere you find this impedance, it's not just an amplifier. If you find an impedance here, you can just make that ungrounded to grounded. You can just inject that current, the current which was going like this horizontally here. Now you're making it to flow through ground, which is your equivalent Z1. At the output port, what I'll do is, I'll put a Z2 here, and I'll see that the same Ik and IL will flow here. And the same I here, and the same I in this direction. So how will you write Kirchhoff's law here? You will write I is equal to Ik plus IL. So now I can confidently say that these two will be equivalent if the same currents are flowing. If the same currents are flowing, that means because there are two nodes V1 and V2, from an ungrounded, I have to create an equivalent two grounded resistors two grounded resistors, one at the input of an amplifier, the other one at the output of an amplifier. So how we can prove this? By simple Ohm's law. See here, why I'm saying is this whole network no textbook will draw. They are going to draw something in the middle, the middle part, the middle portion. See here, only this portion I am going to draw. Only this portion, right? The middle portion I will draw, and I'll prove it by Ohm's law now, right? So I'll put here Z only the middle portion, Z1, whatever current flows here, I, the same we have to inject it down, is grounded. And whatever the current that flows here, I, this will go as IK and IL, the same current should flow here. This is V2. Then what is the relationship between Z1 and Z2? Let me make a statement of Miller's theorem. Now we'll make a heading here. Miller's theorem, right? So what is Miller's theorem? Here the statement is, if an impedance Z is connected between node 1 and node 2 designated as V1 and V2, then it is equivalent to two grounded impedances, Z1 equal to Z by 1 minus V2 by V1 between, this is node 1 and between node 1 and ground, and Z2 equal to Z by 1 minus 1 by V2 by V1 between node 2 and ground. Node 2 and ground. So we'll have a simple proof by Ohm's law. With Ohm's law, we're going to have a simple proof. So let me mention it once again. If an impedance Z is connected between node 1 and node 2, V1 and V2, then it is equivalent to two grounded impedances, Z1 equal to Z by 1 minus V2 by V1 between node 1 and ground, and Z2 equal to Z by 1 minus 1 by V2 by V1 between node 2 and ground. So just tell me, what is I here? What is I here by Ohm's law? I equal to V1 minus V2 by Z. V1 minus V2 by Z. Right? What is the same I here? The same I here is V1 by Z1. V1 by Z1. So if you solve it, you will get Z1 equal to Z by 1 minus V2 by V1. Z1 equal to Z by 1 minus V2 by V1. Now, from the same figure, from here, what is the same I here? I is equal to V1 minus V2 by Z. V2 by Z. But what is the I in this direction? Please be careful here. If the current goes from plus to minus, V equal to IR. If the current goes from minus to plus, can you see the I in the at Z2? It is going in the opposite direction because that's a leaving current for that IK and IL, right? So for the IK and IL, so that's the leaving current. So this current is nothing but what is the current I? It is minus V2 by Z2. Because of the negative sign, what is Z2 here? It is going to be Z by 1 minus 1 by V2 by V1. Now, this is very, very important. Now tell me, if you have a positive amplifier, that we know that it simulates negative resistance. If V2 by V1 is A, if V2 is A times of V1, then the value is going to be negative. If V2 is minus A times of V1, then the value is going to be positive. Say, for example, I am having an amplifier of gain A, negative. Then what you have to do in the exam, whenever a Z is given, for the same circuit, you have to draw, just remove that Z and draw here Z1. And draw here Z2. Then you are not violating Kirchhoff's law at the input side and the output side. At the input side, what will happen? What did I give you? IK and IL. Yeah, this some, yeah, IX, IY, IZ. Maybe IX, IY, IZ are flowing, and then I is the leaving one, right? Leaving current. So you can imagine there's some currents that are flowing at the input. Instead of flowing through Z, you're allowing it to flow through Z1. Similarly, the IL and IM, which is at the output, instead of flowing there, you're allowing it to flow through Z2. So what is Z1 now? Z1 is going to be, this is V1, this is V2, V2 is A times of V1, sorry, minus A times of V1. Then Z1 is Z by 1 minus V2 by V1. What is V2 by V1? It is minus A, so I have to write Z by 1 plus A. Simple Ohm's law, right? And what is Z2? Z2 is going to be Z by 1 minus of 1 by V2 by V1. And V2 by V1 is minus A, so it's going to be Z by 1 plus 1 by A. So if there is a negative gain amplifier, you're going to simulate a positive resistance. Suppose the amplifier is having a positive gain A. This is V1 and this is V2. V2 is A times of V1. Then it is equivalent to what we have to do in the exam. Just because, see, when we are doing network analysis, these capacitors unnecessarily, they will eat our time. Because of these capacitors, we are forced to draw the high frequency model and then apply Kirchhoff's law. It's a big headache. Instead, just remove that capacitor, but put two capacitors. One here between 1 and ground, and the other one 2 between 2 and ground. And what is Z1? Z1 is going to be Z by 1 minus V2 by V1. But this time V2 by V1, it is a positive gain, so you're going to simulate a negative resistance. And what is Z2? It is Z by 1 minus 1 by V2 by V1, which is A, right? Z by 1 minus 1 by A. So this is very, very important. This is the proof for what theorem? Miller's theorem, right? Now you might ask me, sir, why did you not calculate Z2 till now, before the break? After the break, did you got all the energy, after eating, you came and calculated both Z equivalent at the input and the output. The point is, I was calculating only the input resistance in those problems. So I'm interested only in Z1, right? And the second reason is, what is the value of Z2? If you see the Z2, when the gain is more, suppose A is 10 lakhs or A is 100 or 1000, your Z2 is approximately equal to Z. So there is no much Miller effect at the output side. Miller effect is more pronounced at what side? Input side. It is not much at the output. So I didn't bother to calculate there because the question itself was calculate Z equivalent. So I was interested in Z equivalent at input. What is Z equivalent at output? Z equivalent at output is Z divided by 1 minus 1 by V2 by V1, right? So let me see whether my statement is correct. If an impedance Z is connected between node 1 and node 2, then it is equivalent to two grounded impedances, Z1 between node 1 and ground and Z2 between node 2 and ground. So the simple Ohm's law, what is this? I equal to V1 minus V2 by R. I equal to V1 minus V2 by R. The simple Ohm's law, we were able to prove a very, very powerful theorem called Miller's theorem. This is something like in mathematics, you have so many theorems, Pythagoras theorem. So what the Pythagoras theorem will do, it'll save time. Whenever you know the two sides in a right triangle, you can directly quickly go and find the hypotenuse, is it not? So similarly, whenever you are doing network analysis and it's a big headache when you look at capacitors that are ungrounded, then what we have to do to calculate the input tau1 and tau2. See here, now it's so easy to calculate tau1 and tau2. If input side you have Z1 or C1, output side you have Z2 or C2. So it's very easy to calculate tau1 and tau2. And then what is the total tau? Tau1 plus tau2. And what is bandwidth? 1 by tau. So it's much easier. So please, 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 my request is you have to remember this formula. Very easy formula. What is the impedance? It is Z divided by 1 minus the gain V2 by V1. 1 minus the gain of the amp. If the gain is positive, you're going to simulate negative resistance. If the gain is negative, you're going to simulate positive resistance. So just 2 steps, 2 Ohm's law equations, and that's it. Miller's theorem proof is done, right? So now we are not violating the Kirchhoff's laws. The current that was entering Ix, Iy, Iz is I now. So the same I took here and the same I here. So now you can understand that this is a small portion of a bigger network. You have a very big network and you are worried about that single element Z or that single capacitor, that single parasitic capacitor that is stuck between the base and collector terminals of a common emitter or the gate and drain terminals of a common source amplifier. So that is really hampering you. Then what we have to do is that simply we have to remove it. See here, example, just an example, right? How we are going to apply is, suppose you have, while calculating, this capacitor is a big problem, right? This is a problem. This is a big problem. There's a big problem, right? How can I make it simple? This is stuck between node 1 and node 2. So what we have to do, there are two students. One student he has replaced the small signal model for the BJT and then he's kept on doing it. There is other student who's very clever, and what he did was he quickly removed this capacitor and he put two capacitors, one between node 1 and ground, the other between node 2 and ground. One is C1 and C2. And here he calculated tau 1 and here he calculated tau 2. And he said that the total tau is going to be tau 1 plus tau 2 and bandwidth is 1 by tau. But the student one, he's just looking, staring at that capacitor, small signal model, Kirchhoff's laws. We kept on doing all the steps. Are you getting? So this is something we are going to apply in future, not. Oh my God, this has come again. Yeah. So whenever you find a network like this, so this is what we're going. So a big problem, we are going to simplify it. Now this is simplified, right? This is utterly simplified. We're just removing that capacitor and replacing by two capacitors, C1 and C2. This is something we are going to do in future. But there I cannot introduce Miller's theorem, because the moment a problem is given, I am promising you that any problem that we do in the class, so it's bandwidth calculation or input output resistance, I'll not take more than 1 minute, right? There I cannot introduce Miller effect and then explain. From now onwards, please revise the basics. From now onwards, the moment you find a problem, you just go and calculate it. That's it. Tau is R into C, or if there are more poles, tau 1, tau 2, then the total tau is going to be tau 1 plus tau 2. And what is bandwidth? Bandwidth is simply 1 by tau. Bandwidth is simply 1 by tau, right? So this is something we are going to do in future. Never mind. Okay. Okay, find R equivalent find R equivalent. Now, how do we solve this? Here we have R, here there is R. But what is the equivalent resistance at this point? At this point, you have R divided by 1 minus V2 by V1, which is 1 plus 5 is going to be R by 6. Then what is R by 6 parallel with R is R by 7 in series with R. So R equivalent equal to R plus R parallel with R by 6. It is R plus R by 7. It is 8R by 7 ohms. 8R by 7 ohms is R equivalent. So this whole network with an amplifier is equivalent to this R1 or Z1 at the input side, right? So when somebody is seeing here, he does not see R2. R2 is somewhere at the output side, and there is isolation between the input and output. It's only the R1 that he is going to see, R1. And who is going to see R2? If you have to calculate the output resistance of an amplifier, then definitely you have to consider R2 at the output, right? But now please, I don't want output resistance, I want input resistance. So I have to see only through the input side. Am I right? Find tau. Find tau. So the same procedure we have to follow now. Now, what is C1 here? C1 is going to be C multiplied by 1 plus A, C multiplied by 1 plus 98, that is 99C. C. And thank you. I've some of the students have helped me in recognizing the problem here whenever the mirror image comes. So I have to press something here which is hiding somewhere, right? So excellent. I've learned one point from you. I don't know if you have learned Miller effect from me. So I've learned something from you. Very good. So, okay. So now when you short the input, you have R here, you have R. These two are in parallel when you see here, R equivalent. And then here you have C, and then the 99C, right? C equivalent. So R equivalent is going to be R parallel with R, which is R by 2. And C equivalent is going to be C plus 99C, that is 100C. So what is tau? Tau is R equivalent into C equivalent, that is R by 2 into 100C, which is 50 RC. The time constant is increased 50 times because of the Miller multiplication. It actually has to be 100, but the resistance has decreased, so the overall value is going to be 50 RC. 50 RC is tau. So this is all about the basics, right? This is all about basics. I repeat, we might need tools like the Miller's theorem, calculation of input resistance, calculation of output resistance, calculation of AV, AI, and AP, right? And all these calculations we are going to do not on the physical transistor, but on its equivalent model. What are the models that we have? We have 4 models, mostly for all the voltage amplifiers, like the op amp, we are going to use the VCVS model. If there are current amplifiers exclusively like the common base, then we are going to use the current control current source model, right? And on that model on paper, whatever the answer we get, we expect the same answer to come when you do it on experiment, right? When you do the actual common emitter on an experiment, so the answer should match. Are you getting? Almost, right? So these models are quite simple, but the VLSI tool says that the exact BJT is not just 2 elements like a resistor and a current source. There has to be around 42 elements, the noise modeling and all that stuff. So a VLSI tool will do, but in textbooks, everything is simple. A transistor means 2 elements. Diode means only switch, on switch, off switch, on switch, off switch. This idea we will get from the characteristics. And then we apply Kirchhoff's laws and we do rectifiers, peak detectors, clippers, clampers, and so on, right? But 90% of analog discussion runs on amplifiers. Please remember, in amplifiers, what are the three important parameters to calculate? One is gain, the other one is the impedance matching, input and output resistance, and the last one is the frequency reach, tau and bandwidth. That's very complicated bandwidth calculation if you go by the textbook way of doing it, right? The textbook way of doing it, right? Every textbook does that in the first page. But if you go inside the book, then they'll say that there is something called the best approximation is just to add the time constants intuitively. Just by looking at the amplifier, they just add the time constants, tau, and the overall bandwidth is simply going to be 1 by tau, right? So this is about the introduction basics. So from next class, now we are going to have a question and answer session, right? So you can ask doubts. And after that, tomorrow, we are going to start afresh with the first topic in analog, that is the op-amp. Whenever we start, the moment I connect an op-amp power supply, then your mind should say, okay, this power supply is going to decide the swing limits. Whenever I calculate the voltage gain and the current gain, then you know that I'm calculating for the strength, right? Whenever I calculate the input resistance and output resistance of an op-amp, you know that I want to know about the impedance matching. Whenever I calculate tau and bandwidth, then you know its frequency reach. So I don't have to speak anything more hereafter. Just go, apply it and calculate and ask you, right? It'll be a revision of the first class. Whatever we have done till now, the same thing we are going to repeat again and again and again in future classes until one day you say that, sir, enough, sir. These are the same calculations you've been doing, right? And that is what any author has done, right? You open Cedra and Smith microelectronics book this big, right? So so many pages, but ultimately only these three things. They keep on doing the same thing. And finally, they say that intuitively by looking at a circuit, how will you come to a conclusion without doing? So slowly, once you go inside the book, you realize that you're not doing anything. You give an amplifier, by looking at the amplifier, you can tell all these parameters. So it needs practice. It needs practice. So we will repeatedly do number of problems. With that, you will get an idea, right? Okay, so now we can have a question and answers session. So I want, I'll see that, how can I unmute? హలో వెంకట్, అదే టాపిక్ అయిపోయింది. ఫ్రెష్ టాపిక్ బదులు క్వశ్చన్ ఆన్సర్స్ తీసుకుంటాను. అన్మ్యూట్ చేయి, లేకపోతే టాపిక్ ఇప్పుడు మళ్ళా స్టార్ట్ చేస్తే. ఇంకో హాఫ్ అన్ అవర్. ఓకే, ఇంకో హాఫ్ అన్ అవర్ అయితే తీసుకుంటాను. అయితే ఇది నెక్స్ట్ 25 hours ఉంటుంది. అది 25-30 hours ఫ్రెష్ టాపిక్ తీసుకోవాలి. అందుకే సరే అయితే ఓకే. Okay, then it seems still there is time. It's only 8 o'clock now. For another 15-20 minutes, we'll have the basic introduction of the next topic. And then after that, we can have a question and answer session, right? Okay, so the next topic is op-amp. Because I was told that, some of the students, they want the topic to continue, right? And after some time, we can have a fresh topic. We can have a question answer session. Tomorrow we can continue the same thing. Op-amp, right? So what is an op-amp basically? Op-amp is a high gain direct coupled. Why am I saying direct coupled? Because there are no capacitors. I've drawn the diagram first class. There are no capacitors when I connect one stage with other stage. Directly I'm connecting high gain direct coupled differential amplifier. Op-amp is a high gain direct coupled differential amplifier. So it takes the difference and multiplies by a big number, right? Or let me mention it. Like this. So inside an op-amp, the first stage is some differential amplifier followed by some gain stage. So what is V0? V0 here is A times of VD, and VD is V1 minus V2. V1 minus V2. So what is this V1 and V2? V1 and V2 with this plus terminal and minus terminal in an op-amp. So we have plus here and minus here, right? The plus terminal is called the non-inverting terminal, or the voltage summing node or voltage sensing node, voltage summing node. If you want to apply a signal in voltage form, then you can always use plus terminal. For example, in voltage control voltage source, voltage control current source, if you want to design anything that is voltage control, you can use plus terminal. Anything you want in current controlled amplifiers, you can use the minus terminal, right? The minus terminal is called the inverting terminal, or the current summing node. The plus terminal is called the non-inverting terminal or the voltage summing node. The minus terminal is called the inverting terminal or the current summing node. That, like, you want to add currents, that is fine, or you want to build a current amplifier or a current controlled current source or a current controlled voltage source, trans resistance amplifier, then you have to give input to minus terminal, not to plus terminal. So op-amp has got two terminals. One is for voltage sensing, the other one is for current sensing, right? And V0 is A times of VD. How? I'm going to explain, right? How the plus is only for voltages, minus is only for currents, we will see. Right? An op-amp is having a high gain differential amplifier. So what is the gain A? This A is around 10 lakhs, right? So 10 power 6, or it is around 120 dB. It's a huge gain, huge gain, right? A 741 op-amp has got a gain of 120 dB, right? Now, what is an op-amp? Op-amp, I told you first class, because of its high input and output resistance, op-amp is a VCVS. So, in that big diagram of an op-amp, we are interested in the input resistance Rin or RID, where you sense this V1. Yeah, let me mention that this V1 minus V2 is called what? VD, right? VD. This is VD, V1, V2. And at the output side, It is A times of VD in series with R0. So do you remember this diagram? This diagram I have used last class for a VCVS. Now op-amp does not have any special model. The same model we are going to use for op-amp. RID, R0, AVD. Now there is a gate problem and it's also given in IES, of course. Just tell me, when is V0 equal to AVD? Exactly, V0 should be AVD. This V0 should be AVD here. V0 is AVD. What should be R0 if V0 is AVD? Just tell me, when is V0 equal to AVD? V0 will be AVD. V0 equal to AVD only when R0 equal to 0. V0 is AVD only when R0 is 0. When suppose the examiner says RID is 1K, 2K, 3K, then op-amp will draw current. When this op-amp current IOP, the current drawn by an op-amp will be 0. When op-amp current is going to be 0? Just tell me, IOP is 0 only when input resistance is infinite, right? So what is an ideal VCVS? Ideal op-amp or ideal VCVS should have high input resistance and low output resistance. Because I said ideal, RID should be infinite and your R0 should be 0. RID should be infinite and R0 should be 0. Right? And of course, A is also large. A is large, very large. A is also infinite. So how does the ideal op-amp model look like? Ideal op-amp, it looks like this. This is VD. RID is infinite. AVD. And R0 is 0. 0. Okay. So how are we going to use this op-amp? We are going to use it three basic modes of operation of an op-amp. One is open loop configuration. Open loop configuration. Two is negative feedback. And three is positive feedback. In open loop configuration, we are going to see comparator. Now, in this operation, you will realize that op-amp is not an amplifier. It is called an operational amplifier. But inherently, if somebody asks you what is an op-amp, you have to say it's a comparator. It's not an amplifier. It's a comparator. When it will be an amplifier, it will be an amplifier only when it comes to the linear region of the characteristic. That is only when you give negative feedback. So this I will explain you. The second operation is negative feedback. In negative feedback, you can have both linear applications and non-linear applications in negative feedback. In linear applications, we are going to see adder, subtractor, simple amplifiers, all the amplifiers, VCVS, CCCS, VCCS, CCVS, all 4 types. Differentiator, integrator, simple filters, and so on. In non-linear applications, we have to include diode also. So once we finish all the linear applications, I will introduce diode, and then we can combine op-amp with diode to do rectifier, peak detector, right? These are precision rectifier, peak detectors, clippers, clampers, log amplifiers, exponential amplifiers, and so on. So all these, they come under non-linear applications. So in negative feedback, we have both linear and non-linear. In positive feedback, you can have an operation called a Schmitt trigger, right? Schmitt trigger. So our square wave oscillators, right? Square wave oscillators, all that you can see in positive feedback. And what are linear applications and non-linear? Linear applications include op-amp with resistors, capacitors, and inductors, and non-linear applications are rectifier, peak detector, log amp, exponential amplifier, and so on. See, there's a question why common collector is not going to cry by Miller capacitor. So I will explain you, right? There are 2 junction capacitors, one between the base and collector. They don't experience Miller effect because the gain is 1, right? So what happens if you do C multiplied by 1 minus 1? If you have a positive gain, then you have a negative number. So what happens? You multiply C multiplied by 1 minus 1. It is 0, right? So there is no Miller multiplication for gain 1 because that capacitor might experience bootstrap, right? So all this I will explain. There's some student who asked a question saying that why in common collector which has gain 1, there is no Miller multiplication. When you have a positive gain, then you have a negative number. So it is C multiplied by 1 minus 1. So naturally it is 0. So we'll see that when I take up common collector. Very good. So even without starting BJT, at least we have some idea now as to what is an amplifier, what is the transfer characteristics, and what is that we are going to find, right, in future. What is that we are going to find? All that we have some clarity now, right? So now we can go on and do the calculation. Fine. Now, how do you draw the transfer characteristics? Transfer. This is very important. Because, see carefully, all the op-amp problems can be solved if you understand the transfer characteristics. If you look at the transfers, then the whole story of linear applications, nonlinear, all the adder, subtractor, every problem you can solve by looking at the transfer characteristics. So what is the transfer characteristics of an op-amp? It is simple. I told you the gain is 10 lakhs. Huge gain, right? Gain is very high. And here you have some voltage, plus V and minus V. Or some books will also call the supply voltages as the saturation voltages of the amplifier, plus Vsat and minus Vsat. Suppose this is plus 12 and minus 12. And here the input is Vd. So V0 is a huge gain, 10 power 6 times of Vd. Then how will you draw the transfer characteristics? If Vd is taken on x-axis, your V0 is on y-axis. Because of the high gain, now you know how the slope is going to be right on y-axis. This is plus Vsat plus 12. And this is going to be minus Vsat minus 12. And what is this V0 by Vd, 10 power 6? That is nothing but the gain or the slope, right? The slope is very high. If the gain is 1, you know that it goes in the center with a straight line if the gain is 1 with a 45-degree angle. But now if the gain is 10, suppose this is a gain 1, the gain 10, gain 100, gain 1000, right? So gain 10 lakhs, it's almost on what axis? Y-axis. Now you might think, with this, how I can solve op-amp problems? There's just 3 lines are there, right? So 3 lines, with these 3 lines, what conclusion can we derive, and how this op-amp is treated as such a good black box? As inside there are so many transistors, we are least bothered, but we want to know the behavior of the circuits just by looking at these 3 lines, right? So with these 3 lines, what conclusion can you make? This is the transfer characteristics. Just tell me, forget about V0 and Vd, I'll make it X here and Y here. This is X and Y, and yeah. Simple mathematics. I have a line like this. I have a line. This is plus L and minus L, right? I have 3 segments in the line, right? This is segment 1, segment 2, and segment 3, right? Forget about op-amp. Just tell me, what do you infer from segment 1? What is segment 1? What is the equation of a line on y-axis? What is the equation of a line on y-axis? It is 0, x is 0, right? If x is 0, then y is going to lie between minus L and plus L, right? That is what the segment 1 says. So that means if you assume x as 0 and start a problem, see how beautiful this is, right? We don't know what's happening inside, what are the transistors inside, but we are making an assumption here. What is the assumption? A piecewise assumption. I'm assuming that op-amp is in this piece of the characteristic. So op-amp behavior is just 1 line, right? I'm neglecting the 2 and 3, only the 1 line. And because it's a straight line, it's a linear line, op-amp will allow me to apply the linear methods like superposition theorem, Thevenin and Norton, but actual device is what it is giving a nonlinear characteristic, but still it is piecewise linear, right? It's when I'm making an assumption. I'm saying that x, you're always going to be 0. But what is x at this point? At this point here, this point, x number is not 0, it's increasing, right? But I'm assuming x 0 and I'm starting a problem. So when an op-amp is given, that's the discipline. I'll assume Vd 0 and start a problem. But if my answer is between minus L and plus L, plus Vsat and minus Vsat, then I'll stop it. What happens if it fails? Then I'll go to the second segment. In the second segment, tell me what is the equation of this line parallel to x-axis? What's the equation of a line parallel to x-axis? Right? We say y is constant, right? So if y equal to L, then X is greater than 0. If Y is equal to L, then X is greater than 0. So if my op-amp fails at the input side, I'm making an assumption VD 0, I'm finding V0, then now I have to assume V0. If my V0 is plus VSAT, then my VD should be greater than 0. So something like that, right? I'm going to draw for an op-amp again. Just understand here. What happens in the third segment? Third segment, what is the equation of a line that is parallel to x-axis here? Again, if Y is minus L, then my X is less than 0. If my Y is minus L, then my X is less than 0. So can you believe that all the negative feedback amplifier problems like adder, subtractor, differentiator, integrator, everything can be solved by the first assumption. If it fails, then in Schmitt-Trigger problems, oscillator, all those problems, you can go for this assumption and solve. See how simple. Otherwise, when you look at all the transistor circuit in first class when I've drawn, it just blows your mind. But now what they're saying, we will treat it as a black box, and we know how to tame this guy. He's very complicated inside, but we are going to solve him, like a child's play. We are going to solve him very, very simple. Op-amp solving problems is so much fun because we are taming him. We are saying that, what if you are here? If you are here on the y-axis, then your answer should be between minus L and plus L. You calculate the answer. If the answer falls between minus L and plus L, you have done correct. If it fails, then you go to another piecewise segment. If Y is L, then my X should be greater than 0. If Y is minus L, then X is less than 0. Now you tell me, in the transfer characteristics, this is VD, this is V0 for an op-amp. It's an op-amp. VD. This is your plus VSAT and minus VSAT, which are the supply voltages. Then how are we going to solve op-amp problems? Any gate problem you can solve with these simple assumptions. What is the assumption here? If I assume, always start, please, the same thing, the same discipline we are going to follow even for a diode. If the diode has got two segments, we'll assume that a diode is forward bias and start. What is there? So you might say, sir, is diode forward bias? We don't know. We just assume forward bias. If the current flowing through the diode is positive, we say, yes, our assumption is correct. But if the diode fails to be forward bias, then we go and do for reverse bias condition. So that way, with lines, we are going to solve these nonlinear devices, assuming them as piecewise linear. When they are linear, portion by portion, segment by segment, and you are always working on only one segment at any given time, then it allows you to apply Thevenin, Norton, superposition. Because what is op-amp now? Op-amp right now is this line, only this line. If he's in this line, then what is the assumption we are going to make? If VD is 0, then your V0 is going to be between minus VSAT and plus VSAT. This assumption is enough for adder, subtractor, differentiator, integrator, everything. Once you know how to solve all of them, and once you come to Schmitt-Trigger, you say that, no, my op-amp is saturating. How do I check the validity, whether it is saturating or non-saturating? Then I will make a second assumption. What is my second assumption? What is a straight line parallel to y-axis? If my V0 is at plus VSAT, then my VD should be greater than 0. What if op-amp fails in the second segment? Then he's probably in the third segment. In third segment, if V0 is at minus VSAT, then your VD is less than 0. So is it not simple, right? Very, very simple. We just make one assumption and see the validity of that assumption. If it's valid, then fine. So with this assumption, we can start building very, very good circuits, right? Amplifiers, oscillators, switches, rectifiers, precision circuits, everything with these simple assumptions. Excuse me. Okay, so the first application of an op amp, very, very simple application, is a comparator, right? Op amp is basically a comparator. V1 and V2 is V0. V0 is A times of V1 minus V2. What if this V2 is some voltage, 3 volt, and here you have Vn. And the gain is 10 lakhs. Say this is plus 10 and minus 10. Now, tell me, if V1 is greater than V2, if V1 is greater than V2, then V0 is 10 power 6 times of V1 minus V2. Or it is 10 power 6 times of Vin minus 3. Vin minus 3. So if V1 is slightly greater than V2 or Vin is slightly greater than 3. Now tell me, what is Vin minus 3? Vin minus, is it a positive number or a negative number? Vin minus 3. Vin is greater than 3. So it's positive. Suppose if this positive number is 1 millivolt. 1 millivolt into 10 power 6 is 1000 volts. Can you expect 1000 volts at output? No. So your V0 is going to be 10 power 6 times a positive voltage. Definitely this is going to be plus Vsat or plus 10. Plus 10 volts. Similarly, what happens if V1 is less than V2 or V2 is greater than V1 or Vn is less than 3? then V naught is 10 power 6 times the negative voltage. This is going to be minus Vsat or minus 10. So this is very simple, is it not? If V1 is greater than V2, then V1 minus V2 is positive, then V naught is plus Vsat. If V1 is less than V2, Vin is less than 3 volt, then V naught is minus 10 volts. Am I right? So what happens if my Vin is a triangular input? A triangular input, it's got a threshold of 3 volts. Then how do you sketch the output? How do you sketch the output? Right? So what does this line indicate? This line indicates that there is 3 volt. The portion above this line is greater than 3, and the portion below this line here is less than 3. So for all Vin less than 3, what is the output? For all Vin less than 3, your output is at minus 10 volts. Minus 10. For all Vin greater than 3, your output is at plus 10 volts. For all Vin less than 3, Yeah, can you hear me now? Yeah, something happened suddenly. Yes. Now, let us once again see here, if V in is greater than 3, your V naught is 10. If V in is less than 3, then your V naught is minus 10. So this is 3. The portion below is less than 3 and the portion above is greater than 3. So finally, for a triangular input, you're able to get a square wave. What if one of the terminal in an op-amp is grounded, and you give a sine wave here, sine wave. And you give a sine wave as the input. Now you can see that this is grounded. So if Vin is greater than 0, if V1 is greater than V2, then your V0 is going to be plus Vsat. If Vin is less than 0, then your V0 is going to be minus Vsat. So this comparator is nothing but a detector. It's called a zero crossing detector. Zero crossing detector. That means it'll show you what is the output. It will show you the output. It will indicate an output flip from plus Vsat to minus Vsat whenever Vin crosses this zero line. As long as Vin is positive, you have plus Vsat. If it flips negative, it goes to minus Vsat. So what is a comparator? Now you tell me, is it an amplifier? An amplifier should not change the shape of the input. My input is sine, but I'm not getting an amplified version of sine. I'm only getting a square wave. So please, op-amp inherently is not an amplifier. It is only a detector. It can tell you whether Vin has crossed a threshold. In the previous example, it's a 3-volt crossing detector, right? If you want to lightheartedly name it, it is called a 3-volt crossing detector because whenever the signal crosses the 3-volt line, it is indicating the output. So now you can give when this LED is going to glow here. This LED is going to glow. Whenever you have a positive voltage, you can have an LED here like this, right? The diode. So whenever there's a positive voltage here, it's going to glow. Whenever there's a negative voltage, it's going to get off. So it's just indicating whether my input is above a certain threshold or below a certain threshold. So what is an op-amp? When you don't give feedback, it's not an amplifier, it is just a comparator, right? It is just a comparator. So this is a nice application of an op-amp to compare two values. What is a comparator in digital? I compare two numbers, if you have some idea. Because this is a question asked for me in an interview, right? My first interview, the examiner, the interviewer rather, he said, draw a comparator. The moment I started drawing op-amp confidently, suddenly there's another guy said, what is a digital comparator? Suddenly I thought, okay, an XOR gate, right? And then an XOR gate is like a digital comparator. An analog comparator is a simple op-amp inherently, right? Okay, so can we go for a question and answer session? So I'll ask one of the hosts to unmute all the students. Venkat?
Hello, sir.
Nana. Unmute Cheva. Yeah, can you hear me now?
ఎవరు సార్ మీరే? Hello,
Hello, sir.
Yes.
sir.
Sir, page number 40F.
Page number 40F. Oh, specs, I forgot my spec. So, yeah, this is one.
Um,
Can you hear me?
yes, sir. Yes, sir.
This one?
No, sir. 40F only.
Okay, can you tell me what was the diagram there? This one? This is 40.
No, sir.
right?
Yes, sir. This one only, sir.
Yeah, this is 40F. Yeah, 40.
Okay, sir. I understood, sir. This one.
Yeah. Any other doubt you have?
I got it now.
Okay,
yes, sir.
fine.
Sir, in Miller effect,
Yeah.
we are taking the current that the current is flowing through the resistor R or Z, something like that. We are not taking the current flowing into the amplifier. Is it because the input resistance is high for
Very good.
VCVS?
Very good. Yeah. Compared with because generally these resistors or capacitors are connected between the base and collector terminals. And just tell me, what is the base current compared with all the other currents in the transistor? It is naturally very small. So that current we can always, that is why when you are applying Miller effect for quick answer, it is called Miller's approximation. What do you mean by the word approximation? Your answers will almost match there, but it's very quick way of solving. Are you getting? Yes,
Sir,
what you said is correct. That amplifier which we are drawing has high input resistance and it draws no current. And the whole current has to flow through the feedback path, the resistor. Yeah.
Okay, sir. And one more doubt is everywhere we are taking for power supply, we are taking equivalent negative voltages. Is there any specific reason to take equal voltages, sir? Plus or minus 12 volts, plus or
No,
minus 10
there's
volts?
nothing
Plus
like
or
that.
minus-
That's a good doubt. Yeah. Suppose I'm drawing an op amp whose plus supply is 10 and the minus is minus 5. Then the transfer characteristics would go between plus 10 to minus 5. These are the swing limits. Good. Yeah, you can take like this also.
Okay, sir.
Yeah.
Okay, sir. Thank you.
Hello.
Yes.
Good evening, sir.
Yeah, tell me.
Sir, I have a doubt in yesterday's lecture.
Okay.
Sir, what is impedance matching exactly? I didn't understand the concept. Sir.
Yeah, impedance matching is before connecting the amplifier,
Yes,
I'm
sir.
having some voltage. Suppose 5 sin T is there.
Mhm.
And my source has an internal resistance of say 100 ohms.
Yes, sir.
This has to be connected to an amplifier. Before connecting an amplifier, separately I checked. When I check here, I'm having 5 sin T. Now, after connecting to an amplifier, suddenly that 5 sin T becomes 0.1 sin T. The moment I say hello, and then I connect it to an amplifier, the signal is missing. Is there any meaning? No. What is the job of an amplifier? To pick that weak signal and then amplify. What if that weak signal becomes still weak? For example, instead of 100 ohms, the input resistance is 1 ohm. Now, you know that in a series circuit, the voltage will drop more where the resistance is more. Out of 101, who is high? 100. So the whole 5 sin T is going to drop across 100. There is no meaning. Instead of 1 ohm, if it is 100 kilo ohm, high input resistance, then this voltage will also be 5 sin T. It allows an amplifier to have the complete signal at the input. So this is impedance matching for input side. What is impedance matching for output side? After the amplification is over, without connecting load, if I get here 50 sin T, what happens when I connect the load here and suddenly that 50 sin T become 5 sin T? Then that is as good as the input, right? So if this R naught here is much less than RL, it's almost like a short circuit, then all the 50 sin T will travel here. So an amplifier should not be selfish. It should be selfless. It has to take all the signal and give it to the load. Just take it and give. to take
Okay.
वो signal लेना है और signal देना है. It has to take, its input resistance should be high. If it has to
Okay.
give, its output resistance should be low for voltage. If it has to take current, input resistance should be low. If it has to give current, its output resistance should be high. It should not be selfish, just amplify and keep it. Don't give it to the load. So our main aim is the signal should be transferred to the load. It has to transfer in two stages. One is input, the other one it has to go to the output. So you need impedance matching at the input and impedance matching at the output.
Okay.
Did I answer your question?
Yes, sir. Yes, sir. That was very correct. And at the starting of the lecture, when we calculated R equivalent and C equivalent, sir, can you go to that question? Calculation of time constant when we did that. Starting.
Yeah, that was only the R1 that we have done, right? R1 was R equivalent.
The third one.
This is all proof.
So it was at the starting of the lecture. Just a few pages.
Yeah. I should learn how to go to the first page now. Oh my God. The first
So you
page.
drag that bar up and then there
Yeah.
will be an arrow.
Yeah, just tell me, what was your doubt? Oh,
So when we calculated R equivalent and C equivalent,
yeah, R equivalent and C equivalent.
we calculated from the middle of the circuit. So is it necessary, or we can calculate it from anywhere, the equivalent, R equivalent and C?
No. The equivalent should always be calculated at the port. For example, you have a network like this. I will put a arrow here. That means you need to calculate between A and B. Are you getting?
Okay.
So between these 2 points, if I connect a voltage here, this is R1 and R2, then you have to say that if I short this guy, R1 parallel with R2. Are you getting what I'm saying? You have to calculate at that port. Suppose this is a network. I put an arrow here. It means that I want to calculate only till here. If I put an arrow here, I have to
When we are
calculate
asked
for
to
the port.
calculate equivalent resistance and capacitance, then how do we know that we have to calculate it from that port only?
Because I've given an arrow at the input side, R equivalent. At the input side, I've given. See, this is the diagram, right? If I give it here, does it mean this arrow is at the input of the amplifier or output? It means it is at the input side. Only R equivalent at the input you have to find. If I put an arrow here, then you have to find output impedance.
But
And
when we
this
were
arrow
solving,
tells, the nearest to that arrow, you have only this line, no?
yeah.
So at this point only you have to find.
So when we were calculating that through the circuit diagram, not this op-amp diagram, there was no arrow, so that's why I was confused.
Okay. You have to put an arrow through that port. Or at least, see, simple, this line is the input line. This line is for the output line.
Yes, sir.
These lines are the supply lines. So whenever I say input, it is understood that it is through this line. Are you getting? Yeah.
Oh, got it. Thank you, sir. Thank you so much.
Okay.
Hello.
Yeah.
Sir, in first last problem you told, no, sir.
Yeah.
Sir, you told for three, no, sir. Square, pulsing, and.
Achha, last class.
Yes, sir. First
Square
day.
wave, pulse, and then we went for sine. Yes.
Step, pulse, and square wave.
Yeah.
You disconnected in 2 hours, no, sir.
I disconnected.
You disconnected in at 1 o'clock, no, sir.
I disconnected what?
You are disconnected at 7 o'clock, sir. You are not told full class.
That's what. No, the full class next day. Next day we started from there only.
No,
I
sir,
have
only
drawn a rough diagram of the square wave, but we don't know where it is swinging. Then in the next class, I have specifically given values there. One is 1 microfarad, the 1 kilo ohm, and the input had a time period of 1 millisecond. And then the exact Vx and Vy we calculated. That was only a rough sketch. There was only a rough sketch. I just took a blind capacitor waveform which shuttling between 1 and -1, just to show you that the height will always remain same in steady state.
Sir, but you are only there, sir. You haven't told pulsing and
Yeah, pulse
only-
and the step I think I've drawn. I'll see. I'll show you. I have that class with me. Yeah, is this the one?
yes, sir.
This is the one, right?
Yes, sir.
This is a pulse one. This step.
Yes, sir.
There's a step input, and then the pulse input. Yeah.
So where is the pulsar input, sir?
This one is called the pulse. This is a step. Step in. This one is called the pulse. Pulse. And this is the square wave. Okay.
Okay, sir.
Yeah. You just go through it. If you have any doubt, you can come back.
Okay, sir. Thank you, sir.
Good evening, sir.
Yeah. Good evening.
Sir, I have doubt. What is the meaning of direct couple?
Yeah. Direct coupled is initially we used to couple each stage with capacitors, and capacitors are very, very difficult to fabricate on an integrated circuit. It's because 1 microfarad capacitors in a common emitter, input side will be 1 microfarad, RE resistor 470 ohms, capacitor 47 microfarad. It is impossible to fabricate capacitors. So then they started in the next generation of amplifiers, when they were doing the integrated circuits, all the amplifiers, they've removed capacitors. As an analog engineer, we should be shy of using inductors as well as capacitors. Only transistors and MOSFET, they used to be there on an integrated circuit. And how they used to couple one stage with the other stage, just the wire, that's it. They just connected. So in an op-amp, suppose a differential amplifier is there. In previous amplifiers, they used to look like this. This is a common emitter. It had a capacitor here, and they used to couple. This is called capacitive coupling. It is called capacitive coupling, all capacitors. But in the present day world, when I teach you, and you see the present syllabus, he specifically mentions differential amplifier and current mirror. That means he's specifically saying enough of all those old textbooks and old problems. They are outdated. Old problems used to have capacitive coupling, and these cannot come on an integrated circuit. On an integrated circuit, we will have amplifiers like this. And when you go for next stage, the next stage will be directly given. Directly given. Are you getting? So directly connecting one stage with the other stage is called what coupled? Direct coupled. This is the connecting one stage with the other stage through a capacitor is called capacitive coupling. So these type of couplings, you can, if you draw this circuit and give it to a fabrication unit and say, give me an op-amp, that fellow will call you next day. He say, what sort of amplifiers you have drawn? All capacitors are there. We cannot fabricate such. Then an op-amp does not come with capacitors. It comes only with transistors and MOSFETs, no capacitors, right? That is why op-amp is a high gain, direct coupled differential amplifier. Op-amp is a high gain, direct coupled differential amplifier. Yeah.
One more doubt, sir.
Yes.
There are two capacitors, like bypass capacitors and DC coupled capacitors, right? So DC coupled capacitors are in series with the amplifier.
Coupling capacitors. You're calling the input coupling capacitor.
Yeah, coupling capacitors. Yes.
Yeah, I mean, these capacitors I will explain in the class when I take up amplifiers.
So can we say these capacitors can be used to minimize the parasitic capacitance caused by
No. These capacitors will affect only the low frequency. These are the series capacitors, and parasitic capacitors are shunt capacitors. Parasitic capacitors decide this. These capacitors will not decide. The reason is, see here, I will draw a common emitter amplifier response. I told you it is low pass, but strictly speaking, it is not low pass. It is band pass actually. It is band pass. Now, a low pass is a good approximation. The reason is upper cutoff frequency is 1 megahertz. Lower cutoff frequency, because of these useless capacitors, it will be 30 hertz. Now tell me, what is bandwidth formula? Upper cutoff frequency minus lower cutoff. Can you do 1 megahertz minus 30 hertz? It is 1 mega only. So it is waste of time looking at these capacitors, coupling capacitors. All these coupling capacitors, they will affect the low frequency, which is very, very small. The bandwidth is decided not by 30 hertz, it is decided by that 1 megahertz. 1 megahertz. So upper cutoff frequency is decided by the shunt capacitors. Coupling capacitors, the series capacitors will decide this. This we will clearly explain. I will clearly explain when I take up common emitter. Why do you worry now? Because we have not started BJT yet, right?
Okay, so
Yeah.
So it will block the frequencies, right?
Yes. The coupling capacitors or any DC is there, it is going to block. You are definitely right.
Okay, so one more doubt, sir.
Yeah.
We said that capacitance becomes very high, right?
If C is large, tau
Correct.
is large, bandwidth is small. I told you.
If feedback is there, then overall capacitance becomes very high.
Yes.
So if we add a coupled capacitor in series, then overall capacitance will be lower, right?
If you add a capacitor in series, that's what I'm saying. You should be shy of using capacitors. Capacitors cannot be used at all on an IC.
Okay.
Your job is, you have to design an op-amp or the BJT using MOSFETs and think about the inherent capacitors, parasitic capacitors. See, these capacitors you don't see. An analog engineer is dealing with only those capacitors who don't see. This C you cannot see. This fellow has capacitors you cannot see. These are physical capacitors you can see. Now your job is to handle those capacitors which you cannot see, analyze them virtually and design a good amplifier. Are you getting?
Yes, sir.
Yeah, parasitic capacitors, you cannot see them. They are junction capacitors. By keeping them in mind, applying Miller effect in mind, you should be a good designer, not the physical capacitor which you physically see. Are you getting?
Yes, yes.
You have to assume that there is a capacitor and what sort of effect it will create on the amplifier, based on which you have to change your design.
Right, sir.
Yeah.
Thank you, sir.
Yeah. Yes. Yeah, so many participants have raised the hand. Attendees.
Hello.
Yeah.
Sir, in page number 40F.
Page number
40F.
40F. Tell me, what was there in that page?
Sir, we applied the Miller capacitance there.
Okay.
We didn't take the C2 capacitance. That means C into 1 plus A, 1 plus 1 by A.
That is at the output side, no? When we are
Sir.
calculating input capacitor, why you are worried about output?
No,
They
sir,
are
we are
isolated.
calculating the tau.
See, input, for calculating tau. For calculating tau, at the output side, there are no resistors, no? So tau is R into C. At the output side, the op-amp output will have low output resistance. I didn't give any resistors there. It's a good doubt. What she's saying is, when you are calculating tau, you were worried only about the input. You didn't worry about the output for that last problem. Yes, you are right. Because at the last problem, I didn't give any resistors. Are you getting?
Yes, sir. So
Yeah.
that we get the resistance as 0.
Yeah, if I give some resistor, then definitely that tau 2 also you have to consider, and tau 1 plus tau 2, you have to do it. That is the total time constant.
Thank you,
Yeah.
sir. Thanks so much.
Next.
Sir,
Yes.
There we didn't take the op amp, sir. Means
That is an op amp only. That triangle is an op amp.
yes, sir. Inside the op amp there will be components, sir.
Yeah, if there is any component, then you have to.
Sir,
Yeah.
sir, we can avoid distortion by reducing the input signal, sir.
Yeah. Come again. We can avoid. Distortion?
by reducing the input signal.
Yes.
Sir, how it is, sir?
No. What I'm trying to say is, if you give a big input, don't expect a big output more than power supply. Suppose my gain is 100. My output is maximum 10. What is 10 by 100? 10 divided by 100, you can maximum give 0.1 millivolt, no? If you increase more than that, more than 10 millivolt, then that 10 millivolt into 100, that is approximately how much? About 10 millivolt into 100, you are going to get 1 volt. Yes or no?
I see. Yes, sir.
So you cannot exceed more than 100 millivolt. 100 millivolt, if you exceed, the output exceeds more than 10, then that is why, to avoid distortion, your input should have a range between minus V by K to plus V by K.
Okay.
Are you getting?
Sir, getting, sir. Sir, another doubt, sir. Sir,
Yeah.
you said that one point in previous year gate papers, the people chosen that option 1 volt. Sir,
Yeah.
it may be 5 volt also, na, sir?
No, if it is within 5, yes, 5 will also be there. If the supply is 5 and you have two options, 1 and 5, then you have to calculate. But in that option, there was only one voltage which is within the supply limits. So they have taken a triangle.
Sir, please explain the zero crossing detector again.
Yeah.
Little bit, yeah.
See, one end is grounded, no? One end is grounded. This is V2. This is V1.
Yeah.
V0 is going to be A times of V1 minus V2. Am I right? And
Yes.
V2 is 0, so it is A V1. So if V1 is positive, V0 is positive, V1 is negative, V0 is negative. Am I right?
Yes.
Now here V1 I am giving a sine wave. So now if V1 is greater than V2, your V0 is going to be, if V1 is positive, your V0 is going to be plus V set. Right? V1 is greater than V2. What if V1 is less than V2? If V1 is less than V2, then your V0 is going to be minus V set. Now,
Yes, sir.
I am making V2 as 0. When I say V2 as 0, then this V1 has to cross this 0 or it has to go down 0. Yes or no?
Yes, sir.
V1 greater than 0. Why it is 0? Because V2 is grounded here. V2 is grounded.
Grounded.
V1 is greater than 0. V0 is plus V set. V2 is less than 0. V0 is minus V. So very simple. You want a zero crossing detector. One of the terminals should be grounded.
Okay. Okay.
If you have a sine wave like this, whenever Vin is positive, your output is going to be plus V set. Whenever Vin is less than 0, what do you mean by less than 0? Less than 0 means negative cycle. What do you
Yes,
mean
sir.
by less than 0? Positive cycle. For positive cycle, you are at plus V set. For less than 0, you are at minus V set. So it is detecting whether you are crossing the 0 line or not. Whenever you are crossing the 0 line, there is a switchover from plus VSAT to minus VSAT, detecting this zero crossing. Are you getting?
Yes, sir. Yes.
Yeah.
Yeah, thank you.
Hello, sir.
Hello, sir.
Hello,
Yeah, tell me.
sir. While calculating for Miller's theorem, we have considered it as an voltage amplifier, na, sir.
Very good, very good.
Sir, but is it is possible to apply Miller's theorem for current amplifiers or trans resistance or transconductance amplifiers?
I have made it very generalized in the final derivation. In the final derivation, what did I say? What sort of amplifier? If it is trans resistance, it doesn't matter.
Okay.
The gain has to be the voltage conversion gain. The gain you have to carry, even if it is a trans resistance amplifier, if you know the relationship between V2 and V1.
Okay.
If you know the relationship between what? V2 and V1.
Yeah.
Then you can directly say Z1 is Z by 1 minus V2 by V1. That's all.
Okay. So
Are you getting?
Yes,
I didn't
sir,
say Z by 1 minus A, where A is a voltage amplifier gain. I'm not making that. Are you getting?
Yeah.
Textbooks
Yes,
will do Z by 1 minus A1. I'm just, in general, I'm saying it is Z by 1 minus V2 by V1. That's all.
okay,
Are you getting?
okay. Yes,
In
sir.
any network, you can apply this.
Yes, sir. Got it.
Yeah,
Sir.
Good.
Sir, and another doubt.
Yeah.
Sir, you have told that applying input and inverting and non-inverting terminal make op amp as VCVS or CCCS like.
Yes, that I have to do next class, sir. After
Yes,
I
sir,
introduce negative feedback, I will have to show you that through plus terminal, I will show you in the coming classes that the input resistance is infinite. Through minus terminal, I'm going to show you there's a beauty called virtual ground. There is a concept you would have heard in college, something called virtual ground. Op amp tries to keep the two potentials same, and the input resistance through inverting terminal is almost zero. The input resistance through non-inverting terminal is infinite. But inherently, what is an op amp inherently? It is a VCVS, it has high resistance. But the moment you give feedback, the whole story changes. The moment you give feedback, series shunt feedback, high-low voltage amplifier, low-high current amplifier, high-high transconductance, low-low trans resistance, high-low series shunt, low-high shunt series, high-high series, low-low shunt. So next class, when I give negative feedback, you might say op amp was a VCVS, but now what happened? Op amp is a VCVS, op amp is a CCCS, VCCS and CCVS. Once you give feedback, everything gets altered.
Okay.
Are you getting?
Yes, sir. So in open loop, it is VCVS and
Very
depending
good,
upon
very good.
feedback.
In open loop, it is VCVS. In closed loop, it can be VCVS, CCCS, VCCS or CCVS. Very good.
Okay,
Yes,
got
you're
it,
right.
got it. Thank you.
Hello, sir.
Yeah.
Sir, page number 6, sir. Yesterday's class.
Yesterday's class, page number 6. Tell me.
Sir, there you have took 1 millisecond, sir. How you got that, sir?
Which one?
In problem, sir. In problem, capacitor 1 microfarad and there is a resistor of 1 kilo. Yes, sir.
Tau, by definition, tau is R into C.
Yes, sir.
Tau, by definition, is R into C. R is 1 kilo ohm. R is 1 kilo ohm and C is 1 microfarad. What is 1 kilo ohm into 1 microfarad? Tau is R into C. 1 kilo ohm into 1 microfarad is 1 millisecond. Are you getting?
Yes, sir. Yes, sir.
Yeah, that is why it was 1 millisecond. And the time period also was 1 millisecond, if I remember. Am I right?
Yes, sir.
That problem. Yeah. That is why e power minus t by tau, for the half period, we got e power minus 0.5 for half period.
Yes, sir. 0.5 millisecond.
Yes. You're right.
Sir, one more doubt is in yesterday's class only, sir, recognizing the type of filter, you have given one table, sir.
Yes.
For omega equal to 0 and omega equal to infinity.
Very good.
There we will draw according to that, sir, open circuit and closed circuit.
Yes, the same procedure I will again follow even for op amp also.
No, sir. How you are taking, I'm not getting, sir. There.
Oh, very good. Inductor will offer an impedance called J omega L. J omega L. Inductor will offer J omega L or omega L. capacitor will offer an impedance 1 by j omega c or 1 by omega c. Now, omega stands for the frequency. If frequency is low, omega is 0, then omega L is 0, which is the impedance. So how do you represent a low resistance or a zero resistance? By short circuit. So this is inductor behavior. For omega infinite, omega L is infinite, inductor will behave like open circuit. But
high resistance
capacitor is,
open circuit.
high impedance means no current will flow. No current means open circuit.
Okay.
Low impedance means short circuit. Voltage is 0, short circuit.
Okay, sir. Got it, sir.
Yeah, short circuit for low impedance, open circuit for high impedance.
High impedance.
Yeah.
And last doubt, sir.
Yeah.
At last, you have explained about comparator, sir.
Yes.
That I'm having some little doubts, sir. Like how you are thinking.
Comparator, what doubt you have?
Sir, two conditions you took, no, sir. V1 greater than V2.
See, I am having an amplifier with high gain. High gain. It is so high that if one voltage exceeds the other even by a millivolt, then your V0 shoots up, it goes and hits, bang, it goes and hits the plus VSAT, the positive rail voltage. If the V2 is slightly greater than V1, slightly greater, even if it crosses by 1 millivolt also, it goes and hits the negative voltage. So op amp, it's so difficult for this op amp, to control him. If V1 is, suppose V2 is 5 volt, V1 is 5.000001. What happens? V1 minus V2 is 0.00001. And that multiplied by 10 power 6. Bang goes the output. The output is going and hitting that plus VSAT. So the op amp, I've drawn transfer characteristic. It works either at plus VSAT or minus VSAT. It is so difficult for him to bring to the linear region. But when you give negative feedback, what is negative feedback? It's something like you have to maintain 0, right? Next class I will tell you, in negative feedback, it's like when you're traveling on a city bus. Suppose the driver applies the brake.
Yes.
Suddenly, what will happen to you when you apply the brake? You just move forward, right?
Yes, sir.
And what happens? Your friend just pushes you from behind in the opposite direction.
Yes.
Then
Sir.
you might not fall because you're moving in towards the driver, and that fellow is behind you. He's just pushing you back, and then you become stable. Are you getting?
Yes, sir. Yes, sir.
Right. So it's like almost like a kingfisher flapping its wings. So if it pushes in one direction, it goes back. If it pushes like this, it goes front. If it hits back and forth, you would have seen a kingfisher choosing a fish very, very stable at one point. So when you give negative feedback, you will not know whether V1 should go more than V2 or less than V2. Because when it goes more than V2, the next feedback mechanism says, why are you going more than V2? Come back. Once it goes below, you say, who asked you to go negative? Come back. So there's something like the mechanism in feedback. It's like V1 wants to go positive, but V2 will not allow. And suddenly it goes negative. So finally, that will maintain at 0. The V1 and V2 terminals are going to maintain 0. So there's a beautiful mechanism. We are going to see this, in next class. But as long as you maintain VD 0, your output is definitely going to be within plus VSAT and minus VSAT. But see what is happening to an op amp. The moment V1 is greater than V2, chunk, it's going to plus 10. And V2 is more than V1, it goes to minus 10. So it's so difficult. The comparator tells you that it's so difficult to control an op amp. Are you getting?
Yes.
Yeah. So next class we will say, come on, V1, don't cross V2. Don't go positive, don't go negative, stay where you are. If you stay where you are, then I can design an amplifier. I can design amplifier, oscillator, amplifiers, adder, subtractor, differentiator, integrator, everything only when he maintains that 0. Because what happens when you slightly increase it? When the VD goes positive or negative, see, what is the point? I'll tell you, let's apply some logic. I have 10 volts with me. I've given to op amp. and then op-amp output is also giving 10 volt. Then what a student will think, sir, already you have 10 volt, the same 10 volt is coming at the output, then what is the need of op-amp? Yes or no?
Yes, sir.
See, supply is 10, what is the output? 10. So the same output is coming, what is the need of an op-amp? So that means comparator is not an analog circuit, it is a digital circuit. The output is giving logic 1 or logic 0. That is not at all an analog circuit. So op-amp inherently is a comparator. It is digital. It gives logic 1, logic 0, logic. It is utter useless to use op-amp in open loop. Are you getting? Because he is not an amplifier, he is just a comparator.
Okay. Sir, in this graph, we can get that in place of 0, it can be in place of 1, sir.
You want to shift this 0 to 1?
Yes.
So why you want to shift it to 1? If you want to shift it to 1, that's called the offset. See, then tomorrow when a sine wave is there, I will have a sine wave with some DC. Are you getting? So why do you want an offset?
No, sir, in question they might ask offset, like I was asking.
Yeah, if offset, that is my last topic. Even if offset is there, how much is acceptable, what we have to do, how much we have to nullify, all that we can see there. Okay?
Okay, thank you, sir.
Yeah.
Hello, sir.
Yeah.
Sir, while calculating the time constant, third example, sir.
Like
we have two capacitors, no, sir?
Yes.
How did you take the point between the capacitor and the resistor, like port, while calculating?
How did I calculate it? See, my point is, I have to treat that circuit as if there is one resistor and one capacitor.
Okay, sir.
So left side, I took all the resistors into one resistor, and right side at that node, I took all the capacitors as one capacitor, and then I try to combine them. So that is the correct place for calculating tau, no?
How should we choose?
Okay, suppose you have chosen other points. How will it be? Suppose you have chosen after the first resistor. Then one resistor will be there, some capacitors will be there. That is wrong, no? That is not an equivalent resistance. Suppose I want an equivalent resistance. 5 resistors are there in the diagram. Can you take 3 and leave 2?
No.
No. You have to combine all of them. Where will you combine all of them? Only at that point which I have shown.
Okay, sir.
Are you getting?
Yes.
There you can combine all resistors in the left side, all the capacitors in the right side.
Okay, sir.
And
sir,
then
there is an option.
One resistor and one capacitor. See, simple. I'm drawing it here. Can you see the diagram?
Yes, sir.
Yeah, this is a diagram. Okay. This is a diagram. Now I want a time constant for this circuit. What's the circuit? Where will you choose? Here all the bunch of resistors are there. Here all bunch of capacitors are there. You have to see here, no? Yes or no?
Okay.
Because all these are one resistor group, this is a capacitor group. What if you choose here? Some resistors are there, then can you say this I'm getting an equivalent capacitance seen from here? Are they capacitors? No, they are resistors, right? So you have to combine all these resistors as one single resistor, all these capacitors as one. This you will study, in networks, what is the equivalent resistance seen here.
Okay.
Between the 2 points. That's the logic. Because I want to combine them into 1R and 1C. That's the idea. Are you getting?
Okay, sir.
Yeah.
Thank you.
Still?
Hello, sir.
Yeah.
Sir, I want to give a microvolt signal to op-amp, sir. If I give 2 microvolts, if I multiply with 10 power 6,
then you get 2 volts.
Less than 10, no, sir.
Yes, is less than 10.
What output we will get?
what is the output that you're, what sort of op-amp circuit? Is it having negative feedback or is it having?
For that comparator, sir. For that comparator.
If one end is ground, the other end is having 2 microvolt, ideally you should give 2 volt. But you know, practically what will happen? Practically, the output will still be 10 volts only. Why? The reason is, even if there is a noise of say, 1 millivolt, some noise which you expect, that gets superimposed on the signal, and finally the output shoots to plus Vsat or minus Vsat. What you have said is only an ideal case. I'll give you a practical example. Practically, see here, even if I ground both the terminals, what should be the voltage here? 0, 0. Output will still be saturation. Now you will get surprised, sir. What is this? Because V0 is A times of V1 minus V2. Yes. But this V1, what if there is some noise superimposed? Then definitely if it picks that small noise or some offset there, the output is going to shoot to saturation. Are you getting?
Yes, sir.
But what you said is correct. If I have an ideal op-amp, I give 2 microvolt, gain is 10 power 6, I'm definitely going to get 2 volt at the output. But when will you generate a good 2 microvolt with a source impedance of 0 ohms? Because even if your source impedance is having 1 kilo ohm, 2 kilo ohm, the moment you connect an input, again by impedance matching, that already the signal is dead. It will still die, no?
Yes, sir.
Because,
yes.
Yeah.
Thank you, sir.
Hello.
Yeah.
Hello, sir.
Yeah.
Sir, just after clipping distortion, you told the concept of bootstrap technique, no, sir? Can you please explain that one, sir?
Yeah. See, bootstrap is if you have an amplifier of gain 1 and if you connect a resistor between input and output, V1 and V2, V2 is V1, then no current will flow. What can we do? Why no current will flow? Because V2 is 1 into V1. So in such an occasion, what we have to do, this resistor you have to remove and do the analysis. Because the circuit lifts with its own bootstraps. Own bootstraps means whatever the signal that I give, the same signal is generated from the supply. The amplifier generates the same signal from the supply, and this resistor has got the same signal at both ends. Now you know that current will flow only when there is a potential difference. Here there is no current flowing, current is 0. So you can treat this resistor as an open circuit. Such circuits are called bootstraps. One example I will give you. This is a emitter follower. It is called what follower? Emitter follower. Why is it called emitter follower? Because the output is following the base voltage. The output at emitter is following base. This is a common collector amplifier. Now, if some student puts a resistor just to cheat us, no? He puts a resistor and say, what will happen to the gain? You'll say the gain is still same. He'll think, "Arey, there's extra resistor is there, you didn't calculate." There is no need to calculate because this end and this end experience same voltage. So I'm going to remove this resistor for my circuit analysis. So common collector is still the same when I put that resistor. Just kick that resistor off. Then if he asks you, how did you do that? Then you have to tell him that I have done with a technique called bootstrap, right? So he'll get worried, no? Wow, this guy knows so much electronics. But the point is, when both ends are at the same potential, the current flowing there is 0. When the current is 0, this is as good as an open circuit. So this is an example of a bootstrap circuit. In future, we are going to do that. Are you getting?
Oh, yeah, sir. Thank you.
Good.
Class doubt
Enana, stop Jadama.
Hello.
Yeah.
Sir, like for a positive value of an amplifier, we got simulation of negative resistance. Sir, then it is of no use, no?
It is, yes, it is very, very useful. I'm going to use what is that name of an analog engineer? There's a very popular current source called
Darlington.
What is that guy? I forgot. I'm going to design that. I know the current source, but I'm not remembering the
Darlington pair.
No, not Darlington. There is a guy called not Wilson. Holland. There is a current source called Holland, please, if I don't do it during the op-amp session, you please remind me. There I'm going to simulate negative resistance and show you, right? It's very, very interesting. Simple. I am going to take an amplifier of gain 2. That's all. What is there? I'm going to take an amplifier of gain 2. I'll give V1 here. This is going to be 2V1. And I'll put a resistor between input and output. Then my equivalent resistance is going to be R divided by 1 minus 2, which is minus R. Are you getting? This I'm going to show you practically.
Okay, so sir, and the second doubt is that, sir, means like we did for this Miller's that impedance is given above amplifier, no?
Yes,
Sir,
yes, ungrounded. Ungrounded.
One impedance, it is ungrounded. Then if there are multiple, means like Z1 above that, Z2, Z3, then that combination we will solve, then we will use Miller's theorem.
Yes,
no?
yes, yes, you're right. If we have some parallel combination of resistors, make them as one, and then you use the Miller theorem. Yeah.
Okay, sir. Okay.
Good, good.
Thank you, sir. Thank you.
Yeah. Can we wind up? My daughter is coming.
Hello, sir.
Okay. Right then. Thank you very much. Yeah.
Hello.
Yes. Yeah. You still have questions? Shall we wind up for today? Okay, then we'll wind up for today. And tomorrow, please, if some of you, I would have not answered them, keep them in mind. Tomorrow you can again ask doubts after the class, right? Thank you very much and good night. Okay, Nana?
Okay, sir. Okay.
సార్ మెయిల్ పెట్టండి సార్
పెడతా
ఎండ్ కొట్టండి సెషన్
ఎక్కడ కొట్టాలి ఎండ్ Yeah. I have to. సర్లే ఒకసారి ఆఫ్ చేసి ఆన్ చేయనా?
సార్.
Yes.
సార్ నేను ఎండ్ చేస్తానే సార్.
ఏనన్నా?
అదే నేను ఎండ్ చేస్తాను సార్. నేను
నువ్వు చేస్తున్నావు ఎండ్?
అన్న నేను చేయమంటావా?
నువ్వు చేసి ఎండ్ సెషన్.
ఓకే ఓకే అన్న.